This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. I got my co-host Chuck Nice, Gary O'Reilly. How you guys doing?
Hey, Neil, what's happening?
Hey.
All right, this is a StarTalk special edition where every now and then it's just Chuck and Gary burning questions.
Whoa.
This was just for you. It's a gift back to you for being such good co-hosts throughout the year.
Wow.
Every now and then we got to throw it back to you because I know you have burning questions. I think you do.
I'm going to start off with something a little personal because I always wanted to know, after a show a long time ago, you may or may not remember, your colleague from Princeton University, who I believe at the time was the head of the Department of Astrophysics.
Okay.
A friend of yours, not just a colleague.
Because I postdoced at Princeton. I had, and spent another many years there. So I have very good friends and colleagues there, yes.
Yes. So afterwards, we were sitting around and you guys got into this discussion about the true size of the universe. And I tried to follow it, but then you went down a geek hole that was so deep.
Geek hole?
That I was just like, what the hell? And I was fascinated by just why, and I didn't want, of course, I was like just sitting there trying to soak up as much of it as I could.
Right, because that never posted. That was just
that was just the two of you.
Oh, going at it. Okay.
And I was like, I didn't have my phone on set with me because I wanted to pull out my phone and just secretly record and be like, this is how they really talk. You guys were disagreeing ever so slightly. It's not like you weren't saying the universe is this size and he was saying, no, it's this size. You guys were disagreeing very slightly on the size and how you get to the size.
Okay.
And you started talking about, the only thing I understood was redshifting. But after that, there was some stuff, man, that you guys were getting into. So I just want to visit that.
Like, you want a piece of that?
I want a piece of that.
Okay. All right. So a couple of things. All right. If you ask any of us what's the age of the universe, we'll come back at you with 13.8 billion years. That's up slightly from a couple of decades ago,
right?
With better measurements. If you'd asked me 20 years ago, I would have said 13.7 billion years. So it's up slightly when we have better data. All right. When I was in graduate school, we did not know the age of the universe and nor the size of the universe to within a factor of 2. Okay? The universe was either 10 billion years old or 20 billion years old. Two different camps, depending on how they valued the data that was being put forth. It turns out the correct answer was in between those two numbers, as you might expect. Okay. As we narrow down the uncertainty of the measurements, it turns out there are two different measurements of the age of the universe. One of them comes from supernovae that are exploding at. What's good about supernovae is when they explode, they're brighter than the galaxy they're contained in. That's how much energy they're putting out. So you can see supernova basically to the edge of the universe. All right. So they form a good sort of what we call standard candle. All right. Supernovas have commonality among them. You see where one explodes. How bright does it get? How quickly does it drop off in brightness? You calibrate that. You can get a distance to that supernova. Okay. And by virtue of the expansion rate of the universe, you get an age of the universe. There's another method you get by observing the cosmic microwave background. Does not use supernova. Each of those are highly precise methods, yet they do not agree with each other on the size or the age of the universe by a little bit. And you can say, oh, it's just a little bit. No, the uncertainties in each of these measurements precludes the other answer from being correct. Okay.
Damn.
Because we've narrowed the uncertainty. So the point, it sounds, you can have two numbers. Is it 13.75, 13.83? Well, who cares between friends? But if those two measurements are tight, then that's a problem. It's a scientific problem, and it's called tension. It's called tension in the cosmological model. You can Google tension, cosmological tension, and it's unresolved at this point. Last I checked, we can't resolve the difference between these two methods. So either we don't understand supernovae or we don't understand the cosmic background, but we think we do, and therefore we're getting the wrong precision in the answer, or something else is going on that might involve both of them. Or maybe to think about the age of the universe is a question that doesn't have meaning unto itself. It's like saying, what kind of cheese is the moon made out of?
Right.
You could try to answer that question.
No, we know it's Swiss.
All right.
But if the universe is constantly expanding, Neil, doesn't that make measurement irrelevant?
So the measurement would be in this moment, right? In the current epoch. Yes. Yeah. So now, beyond that, because I'm trying to remember what that conversation that you were eavesdropping on was. That could have been part of it. But also, we can say, well, how big is the universe? You might hear some people say, well, it's 13.8 billion light years to the edge. Okay? I've said that. That's a very common thing you'll hear people say. More precisely, and this is where we get into the weeds, that is how long it has taken the light to reach us, emitted by objects on our horizon. Okay?
Right.
But over that time, the universe has expanded. So you can ask a different question and say, how far away is that object today? You can't see it today because its light hasn't reached us today. It only just released its light today. Okay? How far away is it today? You go back to your equations, your models, and that object is like 46 billion light years away in that direction. And then that horizon goes in the other direction too. So the total size of the observable universe today is nearly 100 billion light years across. Right, today. But we don't see that. And so I'm raised in you only talk about what you can see camp. And so we see the galaxies on our horizon and we say they're 14.8 billion light years away. Their light was emitted from the galaxy when it was 13.8 billion light years away. So that's what we were hashing out when the cameras weren't rolling, that you rudely eavesdropped on.
Yeah, well, I'm glad I did, and I'll do it again.
Will the universe continually expand, or will it get to a point and go, I had enough?
Okay, yeah. So wait, let me finish something up with Chuck.
All right,
you can say, well, I gave you the size of the observable universe, but how about the actual universe?
Right.
We don't know. I don't know how far beyond our horizon the actual universe goes. Any more than if I plunk you down in the Nina, the Pinta, and the Santa Maria in the middle of the Atlantic, just plunked you down there, you would not know how far the ocean goes beyond your horizon.
Right.
You'd have to sail it and continue to sail it until one day you run out of ocean.
Right.
So
yeah, but that horizon, although it appears to be moving, is actually not. Whereas the universe's horizon is actually moving.
Oh, wait. So our horizon, yes, it is moving outward.
Right.
At the speed of light. Okay. That has nothing to do with the expansion speed. It's the speed of light with which our horizon is growing. So in a billion years, our horizon will not be 13.8. Let's round it to 14. Our horizon will be 15 billion light years away. Okay. The light horizon. And in another billion, it'd be 16 billion. And every next billion years, our horizon is washing over whole other parts of the universe that previously never reached us, whose light had previously never reached us. So here's the freaky part. You get to 15 billion years, what do you see? You're seeing the Big Bang for those galaxies because their Big Bang light is only now just reaching us. So the Big Bang signature is a continual signature that's expanding at the speed of light. Because every next layer of galaxies, you're watching them being born, and then the next one being born, and then the next one, and then the next one. And that's because the speed of light is not infinite. If the speed of light were infinite, you'd have no knowledge of the past. And you know who one of the first people to try to measure the speed of light? Take a guess.
I'm going to say.
Well, maybe people tried earlier, but it's Galileo.
Galileo.
He put two people on mountaintops with lanterns, okay? And said, and when one flashed, the other would open the shutter on one and close on the other. And I love the results of his experiment. He said something like, if it's not infinitely fast, if it's not infinite, it is remarkably fast. Because he could not measure the speed.
Couldn't measure the speed.
But he's a scientist, so he doesn't have a number. It's just faster than he could measure. So he allowed it to be like infinite, or really fast, faster than Giovanni could open the shutters of his lantern on the opposite mountain. So the point is, if light were infinitely fast, we'd see the entire universe all at once, all the time and all at once. So the Big Bang is not some moment in time that happens to be captured by these galaxies and the cosmic microwave background in this moment. That will always be there. And it's not because it's the same thing that's there. There's other galaxies being born that are now giving you their information. And at 15 billion years, the cosmic microwave background that we now see, all of that became galaxies, stars and galaxies. So it's a fascinating time machine that the expanding universe, the extent of the universe, and the speed of light hands us, which is why we have cosmology at all.
Damn.
Now, so Gary, the expansion of the universe, all data points to that's a one-way trip. When I was in graduate school, we were always considering, might we one day recollapse? If you want to recollapse, you need enough mass and gravity to sort of pull it back again. The universe is expanding at the escape velocity of the universe itself. Okay.
So if I think about us as a species and our intentions to go into deep space, okay, that's most likely going to happen at some point in the future. I'm not going to put a number next to it, but at some point in the future. But how are we going to communicate in deep space? I mean, how do we get through to the point where we got reliable, real-time communication between ourselves? I mean, is it even possible, viable?
It's not Star Trek, where they have if we had my what's it called, subspace
communications.
Yeah, there's something called subspace where they can communicate basically instantly, and we have no way to do that. So what I would say is, for example, by the way, this shows up with our rovers on Mars. Those rovers have to be at least semi-autonomous, because we can't say, look out for the cliff. And then 20 minutes later, the signal gets there, depending on where Earth and Mars are relative to each other in our orbits. That's how long it can take the signal to get there. And then it drives off the cliff and you lost your rover. The rover has to know what to not do without you giving it instructions to tell it to not do it. So, and by the way, if it did go off the cliff, you wouldn't know it for another 20 minutes, because then that's when the signal comes back to you. So it's a 40-minute round trip. When the astronauts were on the moon has a 2 to 3 second round trip delay. So the phone call between billed as the most expensive phone call ever conducted between the President of the United States and the Apollo 11 crew on the moon, that had delays. So you can't have witty repartee, right? When you're talking to people in deep space, not even on the moon. You can't say, hey, Chuck, how you doing? And then I got to wait 1.5 seconds for it to get to you. And then the answer. I get that. 3 seconds later, okay, he's okay. Okay, so this doesn't work. And by the way, so bad that is, here's something people forgot about. So bad that is that the delay to our communication satellites is too long to be acceptable in a phone call. Okay? Before we had GPS and before we had cell phone towers, there were communication satellites. We still have them, but they're not used for talking to each other. That you park it between Europe and the United States because they're geosynchronous, geostationary. Okay. So they're so high up, their orbit exactly matches the rotation rate of the Earth. All right? 23 hours, 56 minutes turning. All right, that's the rotation rate of the Earth once and 4 seconds. All right, so it does that. So now you beam something from the United States up to that satellite, which is 23,000 miles up. Then it goes back down to Europe, which it can do because it sees both continents because it's sitting right between us over the Atlantic Ocean. And then it beams back up and back. So that full round trip, it's 23,000 miles up, 23,000 miles down, 23,000 miles back up, 23,000 miles back down. That's basically 100,000 miles. The speed of light is 186,000 miles per second. So that full round trip is basically a half a second. Now, when you have a conversation where everything you say is delayed a half a second before the person replies, you can't, for example, interrupt them. It's like the old days when people spoke on CBs. You just give information, you say over and out, and wait for them to get it, and then they'd speak back. Okay, that's called simplex communication, where it can only take signals in one direction at a time. Then you can have duplex or multiplex. But point is, even that was too slow, which led to, so Elon Musk has satellites that are in lower Earth orbit, so that the time travel up and back is just fine for you to talk on a cell phone. And so these are issues. So that's a long conversation to say, Gary, that these delays are important and they're a problem. You would hope that if you're far enough away, you don't need to talk to Houston. You got all the solutions you need, okay? Or you don't have to speak to them with witty repartee. It'd be really hard for stand-up comedy. You wouldn't know people were laughing.
But is there another means of...
If we don't travel through space until we invent wormholes with this mythical substance that has negative gravitational energy, negative gravitational force to pry open the fabric of space and time. If we move through space through wormholes, then so could communication.
Right.
So if you're on your way to Alpha Centauri on our fastest spaceships today, it would take you 70,000 years. So, and you could be in a generational spaceship and make babies that they grow up, and then they make babies and they grow up and you all die. And then, 2,000 generations from now, then that civilization on the ship arrives. Okay. That's a long time in the future.
Yeah.
And all I'm saying is between now and then we might invent wormholes. At which point we just step past you and wave and say, we'll see you in 35,000 years as we get to Alpha Centauri system. So if we have wormholes, communication goes through it and the communication is instant. Yes. Chuck, burning question. What else you got?
Okay. So this is a very, I'm just going to read you the question, but then you got to break down everything that's a part of it in order for everybody to know what I'm talking about.
Well, this is your day and Gary's day, so I'm at your service. Yes.
Okay, cool.
Okay.
All right. How can a single electron passing through biprisms or slits interfere with itself?
Nobody knows. These are the mysteries of quantum physics. Like I said, and Gary, finish my sentence. The universe is under no obligation
to make sense or care about your gender.
No, the point is, particles can behave as waves and do behave as waves.
Okay, so I get the duality of light in that it's a wave and a particle.
Yes.
Okay, but so first of all, maybe we should tell people what the double slit experiment is.
Okay. So here's the thing. You're looking at electrons coming through, you have this barrier.
Right.
And you put two slits adjacent to one another. 6 inches, it doesn't matter. Just separate them. They're two slits. Then you have a screen on the other side. And you fire electrons into this, and you know where the electrons are. You fire them in, and you'll get 2 points of intensity on the back screen. One in front of one slit, one in front of the other slit. And there's be some fade off to the left and right of that, because some will get bent a little. Okay. That's what happens if they are electrons. Now you don't look at it, and you do the same experiment. On the back wall, you don't see two peaks. You see what's called an interference pattern,
right,
of the variation of light and dark peaks that completely spreads across the projection surface. Because when you didn't look at it, the electron behaved as a wave. And when you did look at it, it behaved as an electron. And so when waves can interfere. So a wave is just what you think it is. It's ups and downs. If you have two waves that are intersecting with each other, there'll be points where the crests match up. You get an extra high peak. Points where the troughs match up, you get an extra low peak. And these just continue. And you get all combinations of the two. And what that looks like, and what we call it in physics, is an interference pattern. And that's evidence that for that variant of the experiment, the electrons were behaving as waves. Now, what does looking at it have to do with it? Because if you're looking at it, you got to shine light on it.
Right.
If you shine light on it, because otherwise it's an experiment in the dark, and you have no idea what's happening at all. The moment you shine light on it, the light interferes with the electrons being waves, and they become particles at that point. And so it's called the observer effect, and the New Age circles want to believe that it's your consciousness that's affecting it. And that's one of the biggest misconceptions that continues.
Yeah, that's ridiculous.
Who was it first discovered this with waves back in the day, way back?
Well, we knew about the wave interference, okay, because you were always shining light on your electrons, but electrons had to be discovered, all right? The electrons were not known in antiquity. They had to be discovered, and then you got to know how to manipulate them, and then you do these experiments. This is all, we are in the centennial decade of the birth of quantum physics. The 1920s was a seminal set of years where quantum physics was discovered. Hubble discovered that we're not the only galaxy in the universe, and he discovered that the universe was expanding. So a lot went on in that decade. So Chuck, we don't know. It just is.
It just is.
It is a correct description of nature. And an important philosophical point, just because we don't know how something works,
right?
Why something works, doesn't mean we can't describe how it works.
Right.
Okay. So you can know things and predict things, even if you don't fully understand what's happening. And that's where we are with quantum physics. It defies our common sense, but so does practically everything else about quantum physics. We don't live in the quantum.
Right.
There's a book called, what's the guy's name? George Gamow, physicist, wrote a book called Mr. Tompkins in Wonderland. And it's a series. And one of the stories is the physical constants are different in his world. So as he's driving down the street, he starts seeing relativistic things happen, and all Einstein's relativity shows up in his rear view mirror, in his front view mirror. Very clever educational tooling there. So one of them, it's quantum physics. So Planck's constant, which measures the things in the quantum, is some much larger value, which means when you walk through a doorway, you end up diffracting just the way particles would. I mean, it's freaky stuff. It's called Mr. Tompkins in Wonderland. It's a whole series. Very clever. And he illustrated, it has fun little cartoons in it too.
The fact that it is real is just very difficult to wrap my head around.
Okay.
And that is, we have kinematic time dilation, we have gravitational time dilation, and these are not perceptions. Because you told me about the atomic clock experiment. And so the atomic clocks are the most precise chronological measurement of time, and we end up with different readings in these experiments. Is time real?
Okay.
Are humans the only species that kind of measure time? Or
no,
quantify it?
particles do. So, for example, you've heard of half-life, right?
Yes.
Of course.
Half-life, okay. At half-life limit, let's make sure we're on the same page. There's certain elements that are radioactive, which means they decay into different elements. Right. You start with a blob of one element, and if it has a half-life of a week, let's say, that means in a week, on average, half of those atoms will have turned into a different kind of atom.
Right.
Yeah.
They would have decayed. And then in another week, half of what remains turns into it. Okay, it's half of a half of a half of a half. And it drops rapidly. It's 2 to the n power, right? So it drops rapidly. Okay. So if you have 10 half-lives, then you have 1/1000th of what was there before left over. Because 10 is it's 1/2 times 1/2 times 1/2 times 1/2 times 1/2, and you get 1024, I think. Right. So it's basically 1,000th of what was there. All right. You can take an element that has a half-life and accelerate it to near the speed of light, and its decay will be delayed by the exact amount that you calculated in Einstein's relativity. And it's not carrying a Timex with it, okay? Or a Rolex. It's whatever internal clock tells atoms to decay, that is affected by relativity. So time is real. Relativity is real. Now, one way to think of it, which Jan 11 has tried mightily to get us to understand, all right? If you have two axes, okay, and one axis is distance, and the other is time, okay? Not distance, it's just space. One is space, the other is time. And they're like right angles to each other, all right? So it's two axes. Now, if you're sitting there going nowhere, you are not moving on the space axis, but you are moving in the time axis, aren't you?
Yeah.
Time is going forward for you.
Right.
Because your lazy ass is on the couch and you're not actually moving anywhere. Okay? Okay. So if you start moving, then the line on this graph that applies to you is not the one that's going straight up the time axis. Because now you are moving from your previous location and now you're in a new location and you're continuing to move. So now as time progresses, you advance a little bit in the space direction. So you have a line that's at an angle right now from the vertical. Can we picture this in our heads?
Of course. Yeah. Okay.
You got it. Okay. Great. So now, Chuck, you've been slow lately. Gary's a former ex-pro footballer. He's going to run while he watch you walk eating potato chips. Okay. He will run. You are both moving forward in time. Yes. But he's moving farther in distance than you.
Right.
In the same amount of time. So his line will be at an even greater angle than yours will. Okay?
Right.
We got this?
So far?
Yeah. Mm-hmm.
Okay. Now, everybody's got to measure the speed of light to be the same. This is one of the great insights that Albert Einstein had in his relativity. Okay? In order for both of you to measure the speed of light to be the same thing, your time coordinates
have to change.
Have to change.
His
Correct.
would have to slow down in order, if speed of light is a constant, his time, which is that, because the speed of light's got to remain the same.
Correct.
So that means his time would literally have to slow down in order for him to observe me eating the
time that you correct.
At the same time. Jesus Christ.
His metabolism, his thoughts, any radioactive material he's carrying in his pocket, his clock, everything. The vibrations of the atoms, everything.
And referentially, for me, everything is exactly the same for me. My time is staying the same for me, okay? But for him to observe me, his time actually has to slow down in order for that observation to
No. So to be more clear, you're watching him.
I'm sorry, I'm watching him. That's what
I said.
I didn't mean that. I said it backwards.
Right. And so so start that.
Go ahead.
So you're watching him, and from where you are, you both want to measure the speed of light to be the same. Exactly. But the only way that can happen is if you see him move slower.
Right. He's got to move slower because his time,
correct.
And it's not like I'm perceiving him to move slower. His time literally has to slow so that he can
make the same measurement.
Make the same measurement that I.
Correct. Okay. Now, as you go at the speed of light, time stops. So that would be that would be a line moving along the distance axis, but not advancing along the time axis. It would just be flat line there. And so therefore a beam of light can get between any two places with zero elapsed time. So a photon particle of light emitted in the center of the galaxy, which was the object of my affection for my PhD thesis, the galactic center, those photons, I will see them travel for 30,000 years, but if you're that photon, you don't live for any time at all.
No time.
That's right.
There's no time.
You are detected in the same instant you are emitted.
Right.
Correct.
Okay.
Right, so got to get truck off the ledge there.
It's crazy. This is, I mean, and seriously, it's so funny because it's okay, forget it. It is mind blowing that, that these are, for the measurements themselves, these are true measurements. You would think that these would be perceptions because you're talking about it being relative to an observer, but they're not perceptions.
Yeah, in fact, observer is an unfortunate word that we still use today.
Yeah, we still use.
We refer to observer and a phenomenon, and people then think it's something to do with you for being human.
Exactly. No. Right. And it really isn't. These are actual measurements,
Correct.
and the measurements themselves are true and correct as they relate to the time and the constant being the speed of light. That's insane, man.
Yeah, it's crazy.
It's just crazy. It's crazy.
Yeah. And another example, we've given it before, but now we have our own private burning question session here, that this phenomenon occurs in the strength of a gravitational field as well.
Right.
So the stronger is the gravitational field, the slower your time moves. So our GPS satellites fly in MEO, right? We have Leo, MEO, and GEO, right? So MEO, middle Earth orbit. And so those are like 12,000 miles up. And so that's high, okay? Yeah. That's farther away than the diameter of the Earth is above the Earth. So they're far enough away from Earth's center that the difference in timekeeping for them is different than it is for us.
Right.
Okay? So their clocks, since they're farther away from it, are moving faster relative to us.
Right.
So when they keep track of time and send us the time, we have to correct it, because we care about the time in our reference frame, which is Earth's surface.
Okay. So who calibrates this? What calculation are they?
We got people. That's why there's a National Bureau of Standards. I mean, they're people who think, you got to be glad they're there, and they're the unsung heroes. You don't even know they're there, and they're figuring this out for you. So, and let me tell you how deep it goes. So, we're on Earth's surface, and we think of it as just one surface. Right. But there's something called the geode. And the geode is the grid that the GPS satellite is actually talking to. Now, in that grid, is the geode you're using for Earth a perfect sphere? Okay, that's a model of Earth's surface, but that's not Earth's surface. Earth is wider, slightly wider at the equator than it is at the poles. The equator is farther away from Earth's center than people not on the equator, which affects which time frame you are in relative to the GPS satellites. If you want to be really, 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 really precise, you have to know where you are on the geode relative between the perfectly spherically modeled Earth and the Earth that's slightly wider at the equator than at the poles. And by the way, we're not only an oblate spheroid, slightly wider at the equators than at the poles, we are slightly wider below the equator than at the equator. So we're a pear-shaped oblate spheroid. And that's harder to model mathematically. And usually you don't care about that level of precision. So typically they just use a spherical approximation for Earth's surface and let the dust fall where it may.
Are we talking nanoseconds here?
Yeah.
Or
no, we're talking about you're one doorway away from where you had intended to be, that sort of thing. But you're usually tracking down an address. And so once you see the address, you're not still using GPS to decide that. You know who needs these coordinates? The military. Because if they're sending a missile via GPS guidance,
that
you don't want
to make a difference.
Yes, the doorway to the left or the right makes a difference.
Yeah,
right.
So they have to know what the exact shape of the Earth is at the point where they're interacting. And of course, GPS was invented by the military, by the U.S. Air Force, now under the control of the U.S. Space Force. Hold on. Okay, so we still have the Air Force. They worry about the air, okay? Space Force worries about stuff that is not moving through the air, okay?
Right.
Those are called satellites and other rockets, all right? Did you complain in 1947 when the Air Force split from the U.S. Army?
Well, no.
No, because you weren't born. But had you been around, would you be imitating who was president in 1947? Who was it? Truman? Would you be imitating Truman and saying, "Well, why have an Air Force when we have the Army who can fully take care of the Air Force?
Air Force
the Army has
cool.
soldiers on the ground with tanks.
Air Force sounds cool. It sounds cool. Truman had it right. It sounds cool. Where Space Force sounds like something that
science fiction-y.
That Seth MacFarlane came up with.
So the entire space branch of the Air Force basically pulled away to become the Space Force, where command and control is different. All there's so much that it's maybe not entirely as different from the Air Force as the Air Force was from the Army,
right?
But it's different enough to justify its own branch. And now they have a seat at the table in the Joint Chiefs of Staff.
Yep.
Gary, we got time for only one more burning question, but it can't just be any question. It has to be burning.
Okay. What is the one scientific breakthrough for you that has shaped the world the most? And maybe what is the next one for you?
That has shaped the current world?
Yeah.
The fact that matter is made of atoms, and atoms are made of particles.
Really?
I don't think anything has shaped the world more than that knowledge and awareness.
That's a really cool answer.
Because that's what gives us electricity.
Yep.
It gives us the nuclear power.
All of our communications.
It gives us our understanding of molecules, how and why they work. It gives us our understanding of the periodic table of elements. Why is it periodic? Okay. All of that comes from that fundamental realization. Because think of it, before then, it's like, oh, I'm a woodcutter. I just care that my wood atoms, you say it's atoms? Okay, I got wood atoms. Fine. I don't care. I'm just going to cut. Okay. Oh, but wait a minute. When you burn wood, what happens? So there it is.
Yeah, that's a really cool answer. I would have never thought of it that way. But that discovery changes everything.
And if I can tell you one other thing, there's some professors at MIT who created a course called Energy, and big fat textbook. Everything you ever wanted to know about energy. Machines, the conversion of energy from one thing to another. This goes on and on and on. Wait, so let me get the book. Hold on a sec. Here's the book. The Physics of Energy. Okay. Robert Jaffe and Washington Taylor. Okay. Two professors. And look how fat the book is. And so I want to read to you my, I wrote a blurb for it. Okay.
A blurb. Is that a technical term?
Yeah, it's a total technical term. Here it is. You ready? And I pride myself on always having the shortest blurb. But this one is about the same length as the others. Okay, so here it goes. Ready?
Mm-hmm.
If your task was to jumpstart civilization, but had access to only one book, then The Physics of Energy would be your choice. Professors Taylor and Jaffe have written a comprehensive, thorough, and relevant treatise. It's an energizing read as a standalone book, but it should also be a course offered at every college, lest we mismanage our collective role as shepherds of our energy-hungry, energy-dependent civilization.
Wow.
And then they inscribed it to me. There's a little inscription there. I'll read that to you.
Look at that.
Dear Neil, here's hoping we don't have to jumpstart civilization anytime soon.
How about that?
Oh, that's very funny.
So I would say a close second to knowledge that there are particles is the fact that we have learned to understand, measure, harness, and transform energy from one form to another. That, in fact, is the backbone of modern civilization.
Which direction do you see human evolution taking in the future? Do we stay biological, head to a transhuman existence, or do we go totally post-biological and just become this super intelligent AI?
I think we will resist, just an opinion.
Of course.
I think we will resist merging technology with our biology. Neurologically, I think we will resist. There's a lot of spoken about this.
Yeah.
I think we'll resist it.
I think you're right.
Because they say, let's put the whole internet on your frontal lobe.
And people are like,
I have the internet in the palm of my hand without the surgery required to open up my brain and stick it there. So I'll take the 10 seconds to find the information I need rather than the instant information that would otherwise be the case.
See, and I want the chip.
I have evidence of this.
What?
Okay? We're old enough. He's not old enough, but you and I are old enough to watch planes get ever faster over the decades.
Yes.
From the Wright brothers up through the 50s. What I'm saying is,
Yes.
you can ask the question, why did we want planes to go faster and faster?
Because we're impatient.
We're impatient, and we want to reduce the time you are in transit between where you are and where you're going.
Yes.
Okay? Then there's a point where planes just didn't get faster. In fact, they're going a little slower today than they were in the early 1970s. It's not uncommon to, cross the Atlantic at 500, 550 miles an hour. My day, it was like 600 miles an hour, 650, okay? So what's going on? Do you really need it to get there an hour faster? When you have 1,000 movies you can watch, you have access to the internet, you can sleep, you can be plied with alcohol and food. Do you really need to get there fast? In that case, the speed, which sounded like a good idea when you're otherwise wasting your time on an airplane, getting from A to B, the moment you were no longer wasting your time, in fact, you were being productive, the urge to fly supersonic evaporated. And so I'm saying, I have access to the internet. You want me to have 1 second access to the internet or instant rather than 10 seconds. I don't know that I'm going to go there if I got to sit under a scalpel and you poke into my brain. So I think we will resist that. That's my opinion.
I think you're right, but I still want the chip because, first of all, you can barely see them, and they can take 4 of them and put them together and just slide it in. And unless Elon's doing it, then I don't want it. I do not want it if Elon is doing it.
I
don't want Elon's chip.
We'll give you access to the internet.
Right. But here's the reason why I want the chip. And I don't mean for me personally. I mean for
a friend.
For mankind. Okay?
For all mankind.
For all mankind. There are certain responses that we have that are neurochemical. There are certain things that we possess that are detrimental to who we are as a species. And the
wiring of our brain.
The wiring of our brain that come out of evolution.
Yes, so go in, fix the wiring, but get your ass back out of my head.
But my thing is that only the chip could actually do that on an ongoing basis.
It doesn't have to be ongoing if you know exactly where the bad wiring is, fix the wiring, and get the hell out of my head. So if I have a phobia or what's the one where you keep doing something repeatedly?
Obsessive compulsive.
If I'm compulsive or a phobia, and one day perhaps neuroscientists will know exactly where that spot is in the head. Go in there, nip tuck, snip snap, reattach, bada bing, we're good. You no longer have a phobia and you no longer have a compulsion. So that's all I'm saying. I think we will resist that. That's all.
So you're talking about improving mental health. What if we now get to the stage where we can improve our biology and start to live that much longer, and then all of a sudden you've become totally post-biological and you'll live for eternity?
No. We will figure out how to manipulate the biology so that it does not age, but you're still biological.
Yeah.
But do you have that transhuman part where you have to have the chips and the bits and pieces and the upgrades?
Why would you need that if we can fix your brain? That's all I'm saying.
But does the brain control every single aspect?
No, okay. There are people with artificial hips and knees and shoulders.
Exactly.
Heads, shoulders, knees, and toes.
That's why I say I don't see the difference.
I think we will resist that. Next question. Chuck, is it your turn?
Okay, here we go. If an unobstructed photon is traveling towards the edge of the universe, but the universe is simultaneously expanding, which it is, and redshifting increases the photon's wavelength, okay? At some point, because from what I understand, the increase in the wavelength actually reduces the energy of the photon. At some point, does the photon just disappear if it just keeps going and going and going and going?
It redshifts to infinity. So, yeah.
What?
So that happens at the horizon of the universe.
Oh, okay.
Yeah. So if we have a horizon where at that place, all the objects are receding at the speed of light.
Right.
Okay. So when the photon sort of catches up with that,
Right.
at that point, it has redshifted to infinity. And it's got nothing for you.
It's got nothing for you.
Yeah.
Wow. So
Yeah.
that's the end. It redshifts to infinity.
Yeah.
Ugh.
Yeah.
If you could bend the laws of physics to your will, what would you change, if anything?
Ooh, okay. So in graduate school, there's a calculation you do where you look at the gravitational constant, which was first proposed by Isaac Newton, but it would take centuries later to measure its value reliably. What is the gravitational constant? It's the thing that's in the gravity equation that tells you how to calculate how much gravitational force you get from how much mass. So the force is proportional to the mass. How do you turn that into an equation? You have what's called a proportionality constant, the gravitational constant. You don't know this, but you've been invoking that ever since you recited the equation E equals mc squared. All that equation says is energy is proportional to mass. How do you turn that into an equation? You need a proportionality constant. That's the c squared, the speed of light squared. And so all of these understandings of how the universe works, where you have something on one side of the equation, something on the other, there's a constant there. Constant of proportionality. You make the measurement. Okay, so one of the calculations we do is we take the gravitational constant and say, what happens if we change it by a little bit? What are the consequences to the universe? It turns out that you run the gravitational constant through your equations of a star, and if you change the gravitational constant by a little bit, increase it by a little bit, it has stupendous consequences on the luminosity of stars. The luminosity of a star is dependent on the 7th power of the value of the gravitational constant. So if I double the value of the gravitational constant, what's 2 to the 7th power? Okay, 2 times 2 is 4, 8, 16, 32, 64, 128. The luminosity of stars would grow by a factor of 256, thereby reducing their life expectancy. The universe would be much brighter,
Yes.
but they would burn their energy faster, and they wouldn't last long enough for planets around them to evolve into complex life. It would be devastating. That's a lesson to us all. If you want to mess with the universe, you got to,
Be prepared.
be prepared for the consequences. That being said, there's a book series called Mr. Tompkins in Wonderland, written by a physicist, George Gamow, a mid-20th century physicist. Brilliant guy. He first calculated that after the Big Bang, you would have a cosmic microwave background, okay? It made a very important calculation. Anyhow, he wrote a series. He wrote for the public, so he's after my own heart here.
All right.
Mr. Tompkins in Wonderland. And each of these books, Mr. Tompkins was in a world where one of the constants of nature was different. So one of them is the speed of light is 60 miles an hour.
Oh, wow.
So he's driving down the street
In the dark.
and he sees phenomenon that you would see only if you went very fast near the speed of light, like in a normal situation. But the speed of light's not 60 miles an hour.
creative is
Very
that?
creative. Yeah. It's beautiful.
Smart guy.
Yeah, and one would be kind of cool is, there's something called dispersion, and it's diffraction, dispersion, refraction. Is what light does as it goes through a hole in the wall or goes around a corner or goes into another medium. If you change the value of Planck's constant,
Yes.
that's the constant for quantum physics, there's a value you can make it so that if you walk through a doorway, you will diffract. It'll affect you macroscopically in the way it previously only affected particles. And so I thought it'd be fun to dial that up just so I can live in the world of quantum physics just for a day.
Now that'd be cool.
That's what I'm saying. That's all those rules are different.
Yeah, that's a completely.
So I would do that just as an amusement park, not as a thing.
Right.
I'm not messing with the laws of the universe otherwise.
That's good news.
Cool.
Yeah, good. Thank you. So our producer asked that question.
Yes.
Okay.
And here's another producer, Lane.
Lane.
We've learned on the show that your position on human evolution is that it was contingent on the extinction of dinosaurs. Is our civilization contingent on the formation of hydrocarbons over millions of years? Did the progression of human energy sources require that we utilize fossil fuels? Could we have gone from wood fire straight to electricity?
Ooh.
I think about that all the time.
Yeah.
I think about, could we have landed on the moon in the year 1700?
Yeah.
For example.
Right.
Okay.
Why not?
Okay. So one of our other producers, Lindsay, and I co-wrote a book called To Infinity and Beyond,
Right.
where we tracked what people were thinking in their day and how far away was whatever dream they had technologically, intellectually, scientifically. In the year 1700s, I want to go to the moon. How would you do that? You don't even have a periodic table of elements yet. How do you do that? Will the material science allow it? Is physics developed? Do you have enough astronomy knowledge? Do you even know what the moon is? So I think about that all the time. Did everything have to happen in the way it did? Because many other factors have to come together. Many other discoveries matter at the same time. So one cannot just run off by itself.
No. And they all build upon each other.
They all build upon
Like a sliding doors scenario where everything has to happen, or at that moment if you're going through it.
See, that's what I don't agree with that. No. I agree that they are definitely platformed where they build on top of each other, and they have to be made so that that can be done. But I think it's a matter of human beings have progressed and regressed, and progressed and regressed. And if we had just progressed, I think we might have got to the moon long before the 1700s.
Well,
you know, because when
okay.
you think about it, we built the pyramids, we had civilizations, great civilizations, but then we always have war, and that
is the regression.
Slams us back to a place before we started. So we take one step forward and 3 steps back.
or does it? Let me read for you.
Oh,
Uh-oh, here we go.
he's got his phone out.
Let me read
We're in
for
trouble.
you
Go ahead.
a passage written by Christian Huygens,
Huygens.
Dutch polymath.
Okay.
Okay, he discovered what Saturn's rings were.
Oh, cool.
But before him, they were just like blobs of light, right?
Yeah.
So this is a ring system, it's rotating. Exactly. He's done a lot of brilliant things. I'll read to you from his book, Cosmotheros,
Cosmotheros.
1898.
Oh.
Okay? The vices of man are no hindrance to their being the glory of the planet they inhabit. And he's deeply religious. All the scientists back then were
Yeah, of
religious.
course,
Okay,
yeah.
so
Right.
it's folded in here, but watch how he says it. Besides, the vices of men themselves are of excellent use. These are the vices that you said regress us.
Okay.
Are they not?
No.
Excellent use, and are not permitted and allowed in the world without wise design. For since it has so pleased God to order the earth and everything in it as we see it is, for it's nonsense to say it happened against his will or knowledge, we must not think that those different opinions and that various multiplicity of minds were placed in different men to no end or purpose, but that this mixture of bad men with good, and the consequence of such a mixture as misfortunes, wars, afflictions, poverty, and the like, were given to us for this very good end, for exercising our wits and sharpening our inventions by forcing us to provide for our own necessary defense against our enemies.
Saturn notwithstanding, that guy's an idiot.
And by the way, he goes on.
I'm
talks
sure he
about
does.
Poverty,
Right.
what role that plays.
But he's taking kind of a fatalistic view.
Yes,
it's a bit more like his thing is kind of like, we're here because we're meant to be. And he's right in a lot of ways here, especially since I wrote a whole book on this. Okay, Accessory to War: The Unspoken Alliance of Astrophysics and the Military. What's going on when we're at war? Innovation happens. Always.
It's the I don't want to die driver.
Always.
The I don't want to die gene.
And I'm cool with that.
I'm
saying your book is smarter than that guy because
I'm not value judging it.
Because self-preservation will always outstrip anything.
And he's saying that you would only need self-preservation when you have a-holes trying to not preserve you.
Right.
Yeah,
okay.
When a-holes try to kill you, you kick in high gear.
You kick in high gear. So if we go from burning wood, I don't see us going to the moon without a whole middle piece there where our capacity to generate energy gets greater and greater and greater. And there's a lot written about consumption of energy in the historical record, where people say, oh, America's used so much energy per capita, and we have to reduce that. However, again, I'm just observing this. I'm not value judging it. The history of the world, the greatest civilizations, the ones that were most powerful, however you measure that, were the ones that consumed the greatest amount of energy per person.
Always.
Per capita.
Yeah, you can't rule the world unless you're using up a bunch of energy.
You figure out how to use the energy.
Exactly.
Be it human capital, chemical energy, whatever.
Totally.
Right. So I think we needed ways to develop enough energy in the system to create elements of society that are high consumers of energy, like our transportation system.
Okay.
Think about that. Our airplanes, rockets. You don't have that unless you command energy.
And you're absolutely right. My only caveat, I will say, because I do not disagree with anything you just said. I don't necessarily disagree with Huyven Flavin. My caveat is that if our chief goal were one of enlightenment, we would constantly be seeking a higher level with or without the threat of destruction, the threat of war. We would be training ourselves, and this is part of who we are as human beings, we'd be training ourselves to constantly want to advance.
Except, I think the urge to be enlightened is not as strong as the urge to not die.
Absolutely. I agree with that.
Okay.
So my point is, if that were our chief goal was to cultivate that, we would be able to burgeon that.
The species would have to rethink itself.
Right.
Okay.
And that's my point.
Well, that's such a bad thing, because were we to chase enlightenment to innovate rather than create a 1,000-year war, wouldn't that serve humanity better?
Also, when you think about war, think about this. War is very rarely a large swath of a population saying, let's go do this. It's normally a few people making the decision that a bunch of other people are going to go and fight and die.
But they're convincing you that they should do that.
Exactly.
But that's part of the problem here. He just goes on here and says, "'Tis the fear of poverty and misery that we are beholden for all our arts, for that natural knowledge which was the product of laborious industry, and which makes us that we cannot but admire the power and wisdom of the Creator." Again, he's going back to the Creator putting the bad people and the bad things around us, okay? Which otherwise we might have passed by with the same indifference as beasts. And if men were to lead their whole lives in an undisturbed, continued peace, in no fear of poverty, no danger of war, I don't doubt they would live little better than brutes, without all knowledge or enjoyment of these advantages that made our lives pass on with pleasure and profit.
I disagree.
I'm just saying.
I disagree with that.
Yeah, he's saying we're complacent because we have it all. That's basically if it weren't for a-holes,
he said
messing things up.
God put a-holes on earth so everyone else can make life better.
Basically, he's saying God gives you lemons, make lemonade.
The best invention of God there ever was, lemonade.
Yeah. Right.
Okay.
So while we were discussing...
Give me another question.
All right. While we were discussing energies,
yes,
data centers, AI plus Bitcoin mining, energy consumption.
Yes.
It's huge. I mean, this is not just a single nation. This is a global phenomenon. So how are they going to be powered in the future? Is the answer nuclear? Is it solar? Is it wind? Is it burn more wood, burn more gas, burn more oil?
There's no shortage of energy.
I know, but these guys, they can't keep burning up energy like a small nation.
I want to be clear. There's some who walk among us who want to demonize the consumption of energy. And I'm saying, fine, on the assumption that the energy you're demonizing, that the production or utility of that energy somehow badly affects the environment. But solar power, wind power, hydroelectric, there's no shortage of other ways to generate as much energy as you want. You drive through the southwest of the United States, the Sahara, any desert, there are no solar panels there. There's just sand. There's not even plants. There's just sand that gets hot and re-radiates the sun's energy at night. Not serving anybody at all. I'm saying, if you're going to need energy to mine Bitcoin or whatever else there are ways to produce energy that doesn't mess up the environment.
True.
And I don't care how much energy it is, because we're getting more energy than we'll ever use coming down every second from the sun.
And believe it or not, there's energy beneath us. All we got to do is drill a hole down and you can actually pull energy from the earth itself.
I was just in Iceland. They have tubes on the mountainside that go down into the lava, into the very hot layers beneath the crust.
Yeah.
Okay?
Right.
They cycle water down there. It gets hot.
Bring it back up.
Bring it back up. And they send the water down into town. They actually have to cool down the water before it gets to your shower because you get scalded.
Right.
Okay?
But we're going to produce massive data centers.
I don't care.
And they're going to need energy.
Fine.
And we have it. I mean, Neil's saying we have all the energy that we need.
Correct.
And I've been saying this for years. I don't care what anybody says. Okay.
Or just use nukes.
The sun itself is enough energy for any and everything we need. I don't care what anybody has told you. Just because we haven't made the necessary strides to harness that power doesn't mean that power is not available.
Yeah, nor does it mean that we shouldn't think of using things that invoke a lot of it. I don't have a problem with energy.
Yeah, exactly.
No issues.
And this is what I say.
And if you go nukes, you would want to use fusion, not fission. Fission has byproducts you have to dispose of.
Aren't there newer ones coming out, sort of like modular, smaller?
The direction we want to take down in the future is fusion, where there's no unpleasant byproducts.
Yeah,
that would be good.
Yeah, it's just turning hydrogen into helium.
Helium.
That's all that happens there.
Yeah. So anyway,
Chuck, next.
Okay, here we go. In wave-particle duality, we know that photons can kick out electrons, showing that they are both particles, right? We also know that the double slit experiment shows that electrons create wave interference that interferes with itself, so it's a wave, okay? So electrons are waves and particles just like photons, but anybody who's ever used a battery knows how we use electrons for, anything as a particle, all right? How do we use electrons as a wave? Is there anything we do that says we take the wave part of the electron and we use that instead of the particle or as a particle?
Yes.
Yes?
Yes.
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 Okay.
Okay.
Is that the answer? Is that it?
All right. So let me take a back door into your question.
Okay.
All right. So imagine a wave.
Right.
There's it has an up and a down,
Up and a
crest
down.
and a
Trough
trough.
and a crest.
We call that a sinusoid, but it's up and down, like from a sine wave. All right. So if you're using light that has this wavelength and you want to take a photo of anything that has detail that's smaller than that wavelength, you ain't getting it.
Right.
Okay?
Yes.
That light of this wavelength cannot resolve any detail smaller than its own wavelength.
Okay. Gotcha.
Okay?
That makes sense.
That makes sense.
Yeah.
Okay?
Right.
So, how do electron microscopes work?
Aha.
Okay, well, let's look at wavelengths. We get, in order of reducing wavelengths, red, orange, yellow, green, blue, violet. Let's make the wavelength smaller, then we get what? On the other side of violet.
Indigo. No, X-rays, right? Or gamma or something.
Other side of violet. It's beyond violet.
Ultraviolet.
Ultraviolet. Thank you. So red, orange, yellow, green, blue, violet.
Ultraviolet.
Okay. What comes after ultraviolet? X-rays.
X-rays.
Okay. Really small wavelengths.
Okay.
Okay.
More energy, smaller wavelength.
Yes. Not only is it higher energy, smaller wavelength, but if you use that light to take photos, you can see things really tiny.
Okay.
So what you do is you heat up electrons until their wave equivalent is X-rays.
Oh, snap.
And then you beam the electrons to the...
And then you can take pictures of the stuff that's at that wavelength.
The hairs on the edges of insects.
So that's why they call it an electron microscope.
That's why. Because the wave-particle duality is being exploited for that technology. Yes.
So I didn't realize. So that you heat up the electrons.
Yeah,
so
there's a way to do it.
You excite them to the point where they get to that wavelength.
Yes, that's their wavelength.
They have
the energy level where their corresponding energy is X-rays. You beam it in.
Who the hell thought that's brilliant?
This is science. Any electron microscope you've ever seen in any book, that's some detailed stuff.
Right.
You've seen it.
Right.
Like bugs and and cell fibers and things.
Right.
Scary little critters.
I know, aren't they?
Yeah.
And that doesn't work with visible light.
Exactly.
The wavelength is too large.
That's great.
Yeah.
Okay, well, there you go.
That's an example. And
No, that's a great example. All right.
Ready for the next one?
Next one.
Okay, so
These are good questions. You're all good people.
doing our best. Reason we haven't encountered alien life forms now is maybe that these alien life forms are billions and billions of years old and have gone from a biological to an artificial intelligence and are living for eternity, and therefore we can't see, touch, feel. Is that likely as a possibility?
Why wouldn't you be able to see, touch, or feel something just because it lives for eternity?
No, if it's gone to an artificial intelligence and exists in a virtual capacity, if I'm thinking it correctly.
So in using our feeble 21st century vocabulary,
yes,
you're saying it might exist in some computer state, some memory state, and it's just happy existing on its own planet.
Forever.
So
and that's why we haven't had any
So it's living in its own matrix, where it wants to go to the beach. It goes to the beach. What's that movie? Total Recall. Right. Okay, everybody's just living there, and they're just machines humming. Okay. By the way, that was a recurring theme in the Netflix series Black Mirror.
Oh,
okay,
I love
consciousnesses have been uploaded into just this bank of computers.
Who was the British guy that was behind all of that?
I forget his name.
Oh, heavens above. Anyway, moving on.
He's brilliant.
So I'm just wondering, if a civilization, a race, an alien life form has been in existence over billions and billions of years, surely it's evolved into something absolutely superior.
They've learned to ditch their biology.
Yeah.
And pick on. So we could visit a planet where it's just these humming data centers. And that's where millions of people are living out their lives, such as in the Matrix. Okay.
That's plausible?
Okay.
All right. I'll keep an eye out for humming data centers.
But I wonder, how would it ever make a discovery?
Yeah, at that point.
I'm saying, because I still get to go to the beach and pore over the shells and rocks, and I might discover a life form that my consciousness in the box will never know, see, or even think.
Well, if they're really super intelligent, they'll have probably worked a way out.
I don't know how that would be if they're not the ones doing the discovery.
But we're doing 21st century thinking, and they're doing billions and billions
what they
of
would do
years
is they'd have
thinking.
to have some version of itself that's still exploring.
Right.
Yeah.
Out there.
Okay.
So then we might see their hardware emissary.
Interesting, because that's most likely what we'll do once we leave.
That's what we have.
And by the way, why wouldn't they want to leave and go too? Because if you're not bound by the corporeal, then you can now get into a ship.
Bound by the corporeal.
I know, I heard that, and I liked it. I keep
bound by the corporeal.
Well done, sir.
Okay.
Yes, well done. Well played.
You can get into a ship and still be tethered to your planet there, still be on the ship too, and then say, let's go.
Both places.
Let's go both places. Let's go to a black hole. Let's see what the event horizon is.
And you're still back on the planet.
And you're still back on the planet. Let's fall into this black hole.
And that part of you dies, but you're still alive.
That part is right.
Okay,
Yeah.
I like this. This is good.
Yeah. I mean, that's if I could put myself into a that's what I would. That's the only reason I would want to keep living.
If they didn't have probes that went beyond their planet, they would be ossified in the moment that they stopped doing that. This is what I would claim.
See, that sounds like hell to me. Could you imagine being stuck in 2024 for eternity?
Well, if you go far enough back when civilization didn't change by very much, you'd live your whole life with no expectation of living differently tomorrow than you did today.
Damn. Oh, wow.
Whereas today, everybody expects tomorrow is going to be different.
That's true.
Okay, so back then, as far as they're concerned, all of eternity would be like that.
Doesn't everybody think tomorrow's going to be worse?
You know what? That makes a lot of sense why people want to go to heaven. Because if your life changes very little,
you need some escape from that.
Right. And it's like, okay.
If life is changing daily, you got something to look forward to.
See,
Even the
you want a
mystery
rainbow.
is something to look forward to.
You want the pot of gold.
Yes, exactly.
Okay.
Wow.
Go.
Let's go to Alex P. Here we go. You said that there's a time when we will achieve exit velocity from death. Staying on Gary's theme. How does the notion of human immortality gel with the concept of entropy? Ooh, look at that. Do the laws of thermodynamics forbid humans from ever living forever?
Yes, you would never live forever if you were a closed system. Entropy would take its toll.
Right.
But life on Earth is not a closed system.
No, it isn't.
It is open to energy sources beyond itself.
Called the sun.
It's called the sun. Okay? It's that simple.
Exactly.
This is one of the early attempts to out-argue the physics by fundamentalist creationists. They would say, well, you say things always decay to disorder by the second law of thermodynamics, and look at us. We are more complex than ever before. And it's just, you should pause before you try to argue physics with a physicist if your foundational knowledge is from a book written 4,000 years ago. You just have to pause for a moment. Okay. The entropy issue takes place only in closed systems.
Right.
Okay? We have a 3-species sphere downstairs living in a vat of water that is completely sealed. We have kelp, we have krill, and we have snails. And they have been living off each other for 25 years. Since January 1st, 2000, that's 25 years ago, they've been kicking it downstairs. Okay? One of them eats the poop of the other. Okay.
Total symbiosis.
Okay? So, yes, they're symbiotically
entangled.
Now watch. When the construction was happening, the construction folks said, well, this looks pretty important and fragile. Let's protect it.
Oh, they put
a tarp over it. So we caught it early, but, there were a couple of belly-up krill.
Of course.
But basically, they thought that this was its own thing, its own world. It kind of looks that way because it's a sealed sphere, all right? It's not its own world. Right. It requires energy from the outside, just as we do here on Earth.
Great example.
So if you want to live forever, you will do so at the expense of some energy somewhere else on your planet or in the solar system.
Science fiction sometimes has stories of humans interacting with aliens and trying to find a universal commonality, from mathematics or the laws of physics to bridge the inevitable communication gap that would arise between two massively different cultures. Are there any good examples of this you haven't heard in fiction, or any that you were impressed by the authors that they came up with? This question from Brian.
Yes, I have an example.
Brian, our IT specialist.
Our IT guy. Okay,
Yes.
and I got this.
All right.
Very good. Forgive me for not remembering on the spot who came up with this, but it was not a science fiction author. It was like a philosopher, physicist, mathematician.
Sure.
Okay. So he said, here's what you do. If you want to communicate with aliens and you want them to know that we are smart, okay? You just make a triangle, okay? As big as you can on Earth, okay?
All right.
Then you make a square off of each side of the triangle.
All right.
Okay? And the triangle has side A, B, C. These are really crappy squares there. Okay?
We're not judging.
There you have it. Now you make channels here with like fuel or something and ignite it when Earth is at night. Alien will see this and say, we got some smart people down there. Do you know why? Okay. What is the area of a square?
Well, it depends on the size of the square.
No, but if a square of side C, what's the area?
Triangle.
It's I'm trying to remember my stupid geometry.
Well, the area of a rectangle is what?
It's oh god.
It's height times the width.
That's right.
Okay, so a
That's
square.
what I say. Side 1, side 2.
Side times side 2.
Right. Yeah.
Okay, so in a square, so this C was the same as there. So the area of this square is C times C.
C times C.
Sure.
C
That's
squared.
C squared. You got that? Okay.
That's A squared.
A squared.
Yeah.
Okay. A squared. And the area of this one?
I'm going to go out on a
B
limb.
squared.
Yeah.
Okay. If you draw this, it means you know about the Pythagorean theorem.
There you go.
So that the squares of the sides of a triangle are not just an abstract concept, they're actual squares.
That's crazy. Okay.
You light this on fire at night. The aliens will know you've been hanging out with Pythagoras.
Only if the aliens studied geometry.
So I'm saying we all learn the Pythagorean theorem just by looking at a triangle, and we're told that A squared plus B squared equals C
So, but if they were aliens, they'd just look at that and maybe if they were cone heads, they'd like the idea that it was a triangle.
As a kid, the first science museum I ever attended was the Boston Museum of Science.
Okay.
And they had a lot of hands-on exhibits, as good science museums will.
Cool.
And they had this on the wall.
Oh.
And you know what it was? So you would rotate it. So it would be sitting there like this, and there'd be this flat squares against the wall, and this had liquid in it. Just a thin square volume, okay? This had liquid in it.
Oh, that's brilliant.
And so when you
if
turn it,
fills
this liquid fills the other
same
two
volume.
squares, and this then filled completely these
Right,
other
and
two
the other
squares.
two squares. That's
and it would
great.
say A squared plus B squared equals
That's
C
really
squared.
cool, man. That's a great exhibit.
That's some good shit.
Yeah.
That's some brilliant educators
that
thinking
really
about
is.
it.
That's very
sure
good.
are.
And so I was just duly reminded by our producer, Alex P., that Gauss, brilliant German mathematician,
Obviously.
proposed this as a way to possibly to show aliens
Right.
that we're not still living in the caves.
Yeah, because it's so intentional. That's amazing.
Yes.
Yeah. And so simply.
And so simple.
simplistic.
And that's why.
That's the genius of the
That's why.
simplicity.
You're not going to say, you're not going to write an English sentence
Right.
or even some other symbols might throw people off. We can throw our best equation, but they might have other symbols for equations.
wouldn't make a difference.
Whereas a triangle and a square,
They get it.
we got it.
Wow, look at that.
Okay?
All right. There's
you
your
go.
answer, Brian. Chuck, you have a question here, I think.
Yeah, this was like a general kind of.
Yeah.
We'll keep it to this year. My actual question was, what was your top non-astrophysics topic we covered this year, or the favorite thing that you learned in this year?
It would have to be our David Chalmers interview on consciousness.
Oh, okay.
Yeah. He's an Aussie, was that right?
Yeah. But he's NY. I think he's NYU.
Yeah, local,
He is
right.
NYU.
Right. So I just like hearing an expert. So many people are opining on what consciousness is and
Right.
the mind, and he just thought a lot about it. And so I enjoyed learning about, and that was on special edition,
Yes,
not
it
just
was.
any of the flagship StarTalk content. So I like learning stuff as much as I can.
I find that shocking.
You're not the only one.
Yeah.
No, if I'm at a party, for example, and I learn that someone's like an expert on like bird wings or grasshopper legs,
Right.
it wouldn't matter. I got 100 questions for him.
Yeah.
100 questions.
Yeah.
And
Why not take advantage of the expertise?
completely.
Take advantage of the moment. Mm-hmm. Yeah.
All right, Chuck, you want to follow up with your one of
Okay.
yours?
Oh, here's my first question. Is gravity truly a force?
Ooh.
Is it truly a force, or is it just the bending of time itself? Okay, now, so clocks tick more slowly as they are closer to objects with more mass, right? Okay, so if we look at a flat space-time graph, okay, so it's just two axes, all right? And on the space axis, we take Earth and we shrink it down so it's just a one-dimensional flat Earth. So the Earth is now flat on the flat space axis, okay? If you travel up, which is the time axis, right? Which means Earth is stationary.
Yeah, you're just moving in
You're
time.
just moving in time now.
Right. That means you're not moving. You're just sitting there.
You're just sitting there.
yeah.
The time axis then bends, okay? Which means that you're bending space-time, which we know actually happens, but How do we get to that place, in that example? You know what I mean? Like, how do we get to that place in that example? So is it just the large mass object bending time and dragging space along with it? Is that the case? And I left out acceleration purposely just for this. Like, this could never happen, we know. But if it could, how do we get to that?
Well, so let me try
to
answer that. I don't know if I'll succeed. So when you said the time axis is bent, what you mean by that is the amount of mass represented by Earth and its surface gravity has a certain slope of that line.
Correct.
That you would move at an angle, so to speak, on that timeline. And that would be either faster or slower than the time that passes for someone on a more massive object or a less massive object.
Correct.
Okay. I think you shouldn't overthink it. I'm reminded of, if it looks like a duck, walks like a duck, quacks like a duck.
Right.
It's a duck. Okay.
I got you.
All right. So, have we ever talked about the equivalence principle?
In an explainer.
Not in a special edition.
Not
Not a special edition. Let's do a special edition.
All right.
Okay.
Okay. Special edition version of the equivalence principle.
Right.
Okay. So we're here, and I'm on Earth. There's 1g.
Yep.
Okay.
That'd be me.
It's 1g. So all the mass of the Earth is pulling on you for you to then weigh what you do.
Right.
Yeah.
Okay. People say, "Oh, gravity is strong." No, it's not, because I can pick something up away from the Earth.
Right.
And objects accelerate. So if I toss something to you, it won't go straight to you. Gravity will bend it.
Absolutely.
Okay.
So
Got
it's,
that?
Yes.
it's the parabola.
Yes.
Right.
Yeah.
Okay.
Well, on an exam, the answer would be parabola.
Right.
All right.
Once you understood that, then they say the real answer is it's a segment of an ellipse.
Right.
Oh, okay. So,
See,
it's constantly falling?
No. So
No.
if you answer ellipse, it means you know more than the questioner who wrote the question. It can happen, like when they write the New York State Regents in physics.
Okay.
I had to watch out for knowing too much. You have to answer what they think
What they
you should
want.
answer.
Right.
Okay?
They want the answer. That
Yeah. So when you do calculations with trajectories, it's approximated with a parabola. Okay? They don't say approximate, they just say it is a parabola.
Yeah.
For it to be a parabola, it means the force is directly down at every single point on the trajectory.
Right.
Earth is round. So this vertical line is not parallel to this vertical line because it's moved along Earth's arc. They each point inward to Earth's center.
Right.
Okay? You can approximate it over small. This is why people think Earth is flat, because sections of Earth you can approximate with a flat surface.
Right.
But if you did it precisely, you would find that those directions that gravity is pulling you angle towards the center of the Earth, and that shape is not a parabola. It is an ellipse.
Right.
And how do we know it's an ellipse? Because if all the Earth were shrunk to its center, it would orbit the Earth. This ball you threw to your friend would orbit the Earth in a really elongated ellipse.
Okay.
No, it's a cool fact.
Right.
But it's like
All you
crime
have
of
to
knowing
do
too
is
much.
visualize it as, don't look at it as you're throwing something and it's going along the ground. Look at it as you're throwing something and it's going along the curvature of the Earth.
Or the curve that Earth's
Or the
gravity
curve
would
that
give.
Earth's gravity gives you. That's what I mean.
That's it. Okay.
Right.
Okay. And the force of gravity from Earth, when you calculate with it, you put all of the mass at the center of the Earth. And it's so when you say, in Newton's equation of gravity, force equals big G, which is a constant,
Yep.
mass of me, mass of the Earth, divided by our distance squared.
Yeah.
What's our distance if I'm standing on the Earth, which is down in the center of the Earth?
So you two constants.
Yeah,
Your center of mass and the Earth's center
Correct.
of mass.
And that distance is that distance. It's not the fact that there's Earth between it and me doesn't make any difference to the math, it turns out. So, point is, that's why this arc is not thinking that Earth is there. It doesn't care. It just cares that Earth is operating as though it's at its center.
Okay.
And if Earth's surface were not in the way, it would continue in this arc. So here's my point. So Einstein said, if I'm in a rocket and the rocket is accelerating at 1g, okay? That's a pretty fast acceleration.
Right.
That is.
Okay? So 1g in American units is 32 feet per second for every second you're subjected to the force.
Per second.
per second per second. Okay. Right. So after 1 second, you're going how fast?
32 feet.
Per second.
Per second.
After 2 seconds, you're going how fast?
32 feet times 32 feet. No, 64 feet.
64 feet.
64 feet.
Per second.
Per second.
Right.
After 3 seconds?
128 feet. No, 64 times 30. Wait a minute.
96.
See, I'm already.
Thank you. That's the recipe to get you your speed after 3 seconds.
Right. And it will just continue like that. The longer you fall, it just keeps continuing.
It just gets faster and faster and faster. Okay. Okay. So that's Earth's acceleration of gravity.
Right.
Okay. All right. So in fact, well, you're standing here and that's your weight. If I dropped you from an elevator shaft or put you in an elevator and cut the cable, you will fall to Earth at 32 feet per second for every second. So it takes 4 seconds to hit the ground? How fast did you hit the ground?
Wait a minute. This is time. Wait. 32, 64, 96, and then the 32 on top of that.
100,
That's
120.
it. Yeah.
Okay. So, and then you die when you hit the ground.
Right.
Okay.
Or not.
But while you're falling, you're weightless, just so you know.
So it's no good if just before I hit the ground, I jump in the elevator.
If you jumped upwards at 128 feet per second, that would counterbalance the fact that you were falling at 128 feet per second.
I'd hit my head on the roof.
And then you would, I guess, you would just land softly.
It's not a theory I want
you
to
would
test.
be your own retro rocket.
Yeah,
at that point.
that's right. It's your own retro rocket.
Yeah, your own retro rocket.
It's a retro rocket. All right.
Yeah.
So now, Einstein said, now here's a rocket that's accelerating at 32 feet per second. Okay?
Right.
We're in space.
Right.
Okay? You're on the other side of the rocket, and we're accelerating sort of this way, upwards, let's say, towards our ceiling. You're across from me in the rocket, and I take a ball and throw it to you. At the instant I let go of the ball, it is going at whatever speed the rocket was going at that moment, because I'm in the rocket, and my hand is touching the ball.
Right.
But if it takes 1 second to get to you, what happened to the speed of the rocket in that 1 second?
It got 32 feet
went up.
faster.
It went faster, 32 feet. So this ball is not going to make it to you. It's not going to go straight across to you.
No, it's going to go down.
It's going to curve down.
Right. I got you.
It's going to curve down exactly the way it curves down if you threw the ball on Earth. And Einstein said, could you tell the difference between these two situations? In a rocket or on Earth? If the rocket were sealed and just standing here on Earth,
right,
and you perform this experiment, the ball's going to dip before it reaches you. If I'm out in space at 1G, the ball will dip before it reaches you. He hypothesized, turns out correctly, that those two situations are indistinguishable.
So you're telling me someone took a ball on a rocket, for real?
No, there's another way to test this. Okay. These are two different masses we're talking about. One is your gravitational mass.
Yeah.
And that shows up in the FG MM over R squared. Right. The other is your inertial mass, which shows up in your F equals ma, which is another one of Newton's equations. And the question is, are those two masses the same? There have been experiments that have shown they're the same to like 9 or 10 decimal places. Basically, it's a correct understanding of the universe. So, you asked if gravity is a force.
Mm-hmm.
You can think of it as a force when you're sitting here on Earth.
Right.
But when you're just rocketing through space, is it a force? No, it's just the leftover speed the ball had over here that gives the illusion that something pulled it down. But in a sealed rocket, you cannot tell the difference.
Okay.
And so to say, is gravity a force or is it just the curvature of space and time? I'm saying that distinction
is immaterial. It doesn't really make a.
You want it to be.
You want it to be because that is our natural intuitive thought process.
They're experimentally identical.
Exactly. So
and since one of them involves no planet at all,
right?
All we can say is it's convenient to think of that as this thing called gravity here on Earth.
Right.
It's a convenience. In space, it's not gravity, but it's doing exactly the
same thing.
So
but it's not gravity in space.
When did Newton get to his laws of motion?
1687.
So since 1687, we've been trying to break his laws.
No, they're not going to break in the realm that they were testing.
No, but I'm saying people have tried. And they still are holding true.
Oh, yeah. No. It's been verified. So it's only breakdown at the limits.
Right.
Where, oh my gosh, you're really close to the sun. The gravity of the sun is so strong, Einstein matters, okay, in the general theory of relativity.
Right.
And where time begins to get altered. And then Newton's equations fail. They just fail.
Gotcha.
But they still work. We went to the moon on Newton's equations.
Yeah.
Right. So you know.
Yeah.
All right.
So it's like saying, is a hot dog a sandwich? At one point it's just semantic, but people want to argue as though it's a deep philosophical fact.
Right.
It does not matter in the universe.
Right. And the universe doesn't care one way or the other because it works both ways. It's indistinguishable. It works. So basically, this is the spaceship. That's the problem.
And this thing about time.
Right.
Okay? Because I was only just talking about the trajectory.
Right.
So if there's a spaceship going past you, sorry, now let's go back to what's called uniform motion. So it's not accelerating.
Right.
Okay, just easier to think about this. Right. Okay. So a spaceship going past you, you don't know if you are stationary and it's moving or it's stationary you're moving. You don't know.
Right.
There's no way to even determine that.
It's like when you're on a train and it pulls off.
Real slow.
Real slow. The other train you're looking at, you're like, oh, who's moving?
Right, who's moving?
Yeah.
Right, because it's real smooth.
Yeah, right.
Yeah, if it's smooth. In the old days, they didn't have smoothly paved roads.
Right.
And they just had horse-drawn carriages and chariots. And so if you were moving, you knew you were in motion.
Yeah.
So how could Earth be in motion? We would feel it. No, because it's moving through space.
Right.
Not on your damn road.
Right.
Here's the problem. If you want to know how their time ticks, all right, let's say they send out time signals, just one every second. Okay. Well, you'll get one of those signals, okay, and the next signal that comes to you, the interval between those two signals will not match the interval between those two signals sent to you by the person on the ship, because they're coming towards you and they'll be shrunken or expanded.
Yeah.
And so we also know that the speed of light is the same no matter the reference frame. And so everything else adjusts to make that happen.
Right.
And so when Einstein published his general theory of relativity, it took the uniform motion and generalized it to any motion at all, that's why it's called general. The general theory of relativity, which includes accelerations, which then talks about gravity and the curvature of space and time. So that's the best I can do with that answer.
No, that's pretty good. And you're right. The real answer is
you're going to be able to sleep.
You're overthinking it.
Well, yeah, and like I said, on the ship, the trajectory, it looked like a duck, it talked like a duck, it acted like a duck.
Right.
As far as you're concerned, it's gravity.
It's gravity. Right.
Go on about your business.
Yeah. Okay.
Recently, Airbus grounded some 6,000 of its aircraft for emergency computer updates as a result of cosmic radiation. Why was it just Airbus and not others? Is this a one-off for commercial flight, or will this become something that will be a new normal for air travel?
Great question.
You're welcome.
Okay. Okay, so let's back up. There's high energy phenomena in the universe, especially in the centers of galaxies, and that high energy phenomenon accelerates charged particles and to stupendously high energies, like 99.999% the speed of light. They travel across the universe, and especially across the galaxy, and when they arrive on Earth, we call them cosmic rays.
Right.
Okay? They come from every direction. I would see them in my data when I expose a digital detector to the universe through my telescope.
Right.
In fact, there are utilities we have that correct for cosmic rays, because a cosmic ray hits the one of the pixels and it blows it out. Okay? So what you do is you take multiple images and then you
overlay them.
Yeah, you overlay them, and then you take out the high and the low, and you get the median of your images, and that basically takes out all cosmic rays. So when you see images reported, it's not the raw image. Raw image is always contaminated with cosmic rays, and so they're everywhere. Oh, by the way, the cosmic ray doesn't make it to Earth's surface; it hits our atmosphere and creates showers of other particles, who in total equal the energy of that one particle. It's called a cosmic ray shower. You can look it up.
So it's like a diffuser.
It just comes down and it...
See, this is our problem with space travel, the radiation. And now you're telling me this radiation is penetrating.
Well, the total energy does actually reach the Earth.
Yeah.
Okay, it gets,
Right.
but
Just not as cosmic rays.
Not as concentrated.
not as concentrated. Correct. Not as the original
As the
cosmic rays.
original
We
cosmic
still
rays.
call them cosmic rays
Right.
because of their effect on this. All right, this tells you cosmic rays are everywhere.
Right.
Okay. Oh, and high energy charged particles from the sun. We're just right now. We're at the end, recording this at the end of 2025.
Yeah.
We're on the downstroke, the very upper downstroke of the solar maximum. Solar max in the last year and a half or so. And we heard about aurora. Also, the North Magnetic Pole, which when we grew up
Right.
was wandering around Canada, in the last 20 years has made a beeline towards the North Pole. And it just recently passed the North Pole. It's on its way to Siberia. As it goes closer to the North Pole, it actually comes closer to the Northeast. Here we are recording this in the New England, the Middle States, because it just brought it a little closer. All those three factors combined, plus we're monitoring the sun as never before. So we know exactly when it would happen. There was a day you didn't know. Oh, we caught it here. You check it out. Call me if you see. We now know. It's called space weather. There's a whole branch of NASA, if it's still funded as of today, that studies explosions on the sun.
Right.
All right. And one of our favorite guests, Lika,
Right.
she's a NASA solar astrophysicist.
Yes.
And so she thinks about all of this. But anyhow, so we have better predictions, better monitoring. And so there's a greater awareness of aurora today than ever before.
Right.
But there are people thinking, oh my gosh, things are getting worse. But it's not.
Okay,
And this maximum we're coming off of, that max, all they do is counting sunspots when they get a lot and then when they come down. All right. This max was higher than the last max 11 years ago.
Right.
But both of these were lower than the previous three. Okay? So there's nothing, if the sun is going to kill us, it would have happened already.
Oh, yeah, we'd already be dead.
We already been cycles ago.
So
but anyway, that's a long preamble to the fact that it seems to me
Does it?
that given how many planes are flying every day, it's like tens of thousands of flights every day. There's 1 million people at any given moment who are airborne in an airplane. Okay? That many flights that have been flying for that long. Okay? And one plane uncontrollably loses altitude, then regains control. You want to blame that on the universe?
Oh, no, I'm just saying that happened.
No. They said it happened. They blamed a cosmic ray. They didn't know it was a cosmic ray.
I don't know about that because that's not the only incident of charged particles, because when you look at these circuitries,
Yes, of course.
they're so small. It also happened to a car company.
What I'm saying is,
Go ahead.
my chip,
Yes.
in my day, the chips were little.
Right.
About this big.
Yeah.
I take a picture, depending on the length of the exposure, I have a half a dozen cosmic rays that hit that chip.
Ah, I see what you're saying.
Yes, I'm higher up than you. I'm at 7,000 feet. The plane is at 30,000 feet.
Couldn't that
Okay?
make a difference? Because we said that the cosmic rays
No,
come in and hit these other
You're
particles.
missing my point. If you're going to blame it on the universe,
Right.
it would be happening to way more
because
than one plane.
Yeah.
I see. The volume of cosmic
Yes!
rays bombarding the Earth
On top
all
of-
the time.
all the time, on
I get what
top
you're saying.
of-
I got you.
On top of how many flights there are.
Right.
So you have to be so confident
Right.
in the wiring of your plane that the tens of thousands of planes that all have maintenance schedules and all of this, you have to be so sure that there is no human error in any maintenance schedule for any of those planes that are flying every single day. And it happens to one of them, and you say, this plane is perfect, therefore the universe does it.
So this is a
skeptical.
convenient. This is a convenient, I won't say excuse, but I'll
CYA?
say, yeah, because this happened to a car company and they made the same excuse that highly charged particles that bombard the Earth somehow hit the circuitry where it's supposed to go to a 0 or a 1, it changes it to a
Changes
1
the bit.
or a 0. It changes the bit.
Yes.
Okay. And the changing of the bit, of course, changes everything that the computer does
Well,
at that
yeah,
point.
for that
For that calculation.
Yeah.
And so that, but now
so-
that I'm hearing you say this.
So they updated the software. I don't know what they did, but I can imagine what I would have done.
Yeah.
'Cause I've written in my life about 50,000 lines of code. So I think about this, but others, they're programmers who do 100 times that. So I'm not bragging here. I'm just giving some street cred that this is what I would do
Yeah.
if I was worried about this in the future. If it were really a cosmic ray, any truly critical calculation, because planes are flown by computers, here's what I would do.
All right.
If I were the program, because they said they uploaded program. If there's any truly critical calculation that affects the safety of the plane, and the computers are fast, so you can do this in practically real time, I would put a loop in there to do it 3 times.
Right. Redundancy.
3 times.
All right.
Okay? And whichever 2 of those are the same,
That's the right answer.
that's the right answer.
Right. If all 3 are the same, it's the right answer. If 2 are the same, it's the right answer.
Correct.
Right. And if a particle actually kicks something out, changes
Because it's not going to do 2 at
it's
once.
not going to do 2.
Right, it's not gonna do
so,
2.
yeah, the redundancy would cover that.
Correct.
Right.
And
And,
if
why couldn't you just harden the damn...
That's what it's all about. Well, you're hardening not only the software, but also the hardware.
Yeah.
And like satellites know all about this because they're up there above the atmosphere.
they don't have any protection
at all.
Yeah.
No.
It's not just to protect against the radiation, but they're not protected against asteroids,
Right.
meteors.
That's right.
You see, oh, what a beautiful meteor shower. These are these particles
Right.
hit our satellites,
Right.
especially the space station. I
Yeah.
mean,
They have that last message. Oh,
Oh, wow. Okay, cool.
yeah. So
Yeah.
if it's a cosmic ray, that's how I would solve it. I'm glad no one was harmed
Yeah.
in this. I understand it dropped altitude.
See, I was looking at saying, is this a distraction for something else, or is this someone being smart and getting ahead of a story and future-proofing to as much as they can?
Yeah, I think they originally wanted to blame it on the sun because we're near solar maximum and people are have heightened concern.
one on the
But it'd
sun's
be the
gonna see
same
them.
cause and effect. I mean,
Yeah.
the high energy particles hitting your software.
Cool.
Yeah. Okay.
All right. All right, here we go.
You got another one.
Here's another one. What's the most straightforward explanation of the strong nuclear force and the behavior of quarks and gluons? Because they say gluons, and I think like, oh, that's a thing, like a quark, but it's not. It's not a particle, but we call it a name like it is a particle. And then when you think of the strong nuclear force, this should not happen. I mean, I know it's happening on the quantum, but these protons, they're like, yo, what's up, buddy? Come on over here. Let's hang out, man. I love you, man. Like, yo, give me a hug. But the truth is, they shouldn't be doing that. They shouldn't be doing that. You know what I mean?
Because they're like charged
They're
particles.
like charged particles, and they should be like,
They should repel.
yeah,
Right.
straight up turf war.
Okay.
But instead, they're all loving and hugging.
Yes.
Right? But what is the strong nuclear force that this is able to happen?
Okay. So the strong nuclear force is one of the fundamental forces of nature.
Right.
There are 4, basically.
Electromagnetism.
It's really 3.
Right.
There's 3, but
Right.
So just for my benefit, thermodynamics?
No. Electromagnetism, weak nuclear force,
Yep.
strong nuclear force, and then what we just talked about, gravity. Which,
these are the fundamental forces of nature.
right.
And we didn't invent them, we observed them. Okay? And as I
Once
The
again,
opening-
overthinking. See that?
the opening page of one of my books, it says the universe is under no obligation to make sense to you.
Yeah, okay.
Now, here's something to think about.
Go ahead.
The electromagnetic force weakens as the distance separates.
Correct.
Correct?
Right.
Gravity weakens as distance separates.
Correct.
The strong force gets stronger as the distance separates.
Right.
Because
Why did you ask because on the other one?
it didn't come into my head.
Because those other forces we operate, they're in your everyday life in ways that the strong nuclear force isn't. So you can ask, is there anything in your life where if you increase the distance, they are attracted together more strongly? The answer is yes.
A rubber band.
A rubber band,
Yeah.
a spring.
A spring. Yes.
In fact, in physics,
But not a slinky.
if you look at the force equation for a spring, it has a negative sign on it. F equals minus kx is what it is. K is the spring constant. X is how much you have displaced the spring. Okay? The minus means as X gets bigger, there's more of an attractive force back in. Okay? Whereas these other forces, it's a positive. All right? So it's a contest of forces. A proton at a distance sees another proton and say, I'm not coming near you. You can't make me. I say, yes, I can. I'm going to heat up the gas. Now your movements are so fast, you will get closer before you successfully
Repel.
Okay. Okay. The temperature is forcing this. It's like a shotgun wedding. It's forcing it. Then at a threshold temperature, it gets so close. Strong force says, I got you. And the strength of the strong force overcomes the strength of the repulsive force in that instant. Okay. And then it attracts. And then it ain't even about the electromagnetic force at that point.
Wow.
We discussed earlier on about Newton's laws, how that for centuries they've stood the test.
Yeah.
Are we likely to find new or slightly varied laws of nature?
Well,
as we explore the
ideally,
universe?
every time that's ever happened, it's like, oh my gosh, look how much more we now understand when we were previously just touching the elephant, not knowing the animal. So there's a lot we don't understand today. The nature of dark matter, the nature of dark energy, what was around before the universe. Was there a multiverse? How will the universe end? Is there a big rip? These are questions that are just dangling there.
How about time?
Possibly, the time, I'm going to quote Einstein, time is defined to make motion look simple.
Whoa. That's very elegant.
Yeah, and deep. Yeah.
That is really cool.
Okay, so quarks are what protons are composed of.
Right.
As are neutrons,
right,
by the way. And quarks have charge.
Yes.
I don't know if you knew this.
Yes, I do, but I'm not sure if I understand them because when I was reading about it, first of all, there's like, Jesus Christ, like 13 or 16 different kinds. And
No, there's 6 kinds of quarks.
6 quarks. And then, but then there's another levels, and then there's
6.
spins. Well, maybe I'm thinking about
6, yeah.
It's like 2 up, 1 down.
Then, right. So in a proton, it has a charge of +1. Right. And it has 3 quarks.
Right.
So it has 2 up quarks. I think it's up. With a charge of +2/3. What's 2/3 plus 2/3? Each of them has a charge of
1/3.
plus 2/3.
2/3 plus 2/3.
Yes.
Is.
Come on, help him out here.
4/6, which is 75.
No, it's not 4/6.
Then it's not.
Well, you don't add up the denominator.
Denominators. No.
Yeah. Denominator carries, you add up the top. So just do that. 2/3 plus 2/3 equals
1 1/3.
4/3.
1 1/3.
1 1/3. Right.
Okay. So the other quark has to have what charge for it to be +1?
2/3.
No.
I mean, has to be a minus.
Minus
has to be
what?
a -3rd.
-1/3.
Right.
There it is.
-3rd. And then it cancels out, and now you're good.
Well, then it adds up.
It adds up to 1.
Correct.
Right. It cancels out, adds up to 1.
Correct. And a neutron has, I forgot exactly what, but they cancel out to 0 charge. There's like plus 2/3, -1/3, -1/3.
Okay.
Okay.
And then
so there's still charges within there's still charges there.
Gotcha.
All right. Now, so the quarks are fundamental. Protons and neutrons are not fundamental.
One, and then the electron is a negative charge.
No, forget the electron.
Okay.
We're not talking about that.
I know we're not even talking about it. I'm just
electron
thinking,
only knows electromagnetic force.
Right, that's all it knows.
Okay,
right.
and a weak force. Yeah. But the strong nuclear force holds the quarks together.
Gotcha.
It's the strong nuclear force that when you pull 2 quarks apart, you have to get more and more energy to do that, like the rubber band, and then it snaps, creating 2 extra quarks. Right. All right. So that's the strong nuclear force at work. And the spillage out of those particles to attract the other nucleons. So the spillage of the gluon, did I say gluon yet?
Yes, well, we didn't get to them.
Sorry. So the quarks are held together by the strong nuclear force. What propagates the strong nuclear force? It is the gluon. What propagates the electromagnetic force? It is the photon.
Right.
So there's something called a virtual photon that gets passed between 2 objects if they have a charge, and they will feel that and respond and either get repelled or attract. And they're called virtual photons. The photon is the force carrier of electromagnetic energy. And the gluon
is the force carrier of the strong nuclear force.
Of the strong nuclear force. And it's strongest within those particles, but enough spillage so that 2 protons can stick together in a nucleus. But the real action is inside the particle itself.
Wow.
Yeah.
Damn.
I know.
Happy now?
Yeah, it's weird.
It's freaky.
All right, should we have another
Please,
question?
please.
Right. This is from Tamsin, one of our producers.
Tamsin.
Yeah. When approaching a astrophysics problem, how do you determine which mathematical equations to use, depending on your approach or on which aspect of the overall problem you're looking at? Do you shift the equations you use? Just explain how you apply all the equation. Tamsin says thanks in advance.
Okay, great question.
Of
Great
course.
question. So I remembered learning physics for the first time. And a lot of it is kind of like it's a sliding brick on an inclined plane.
Mm-hmm.
There's a pulley. These questions don't look relevant to anything. I wanted to understand the universe, and physics is fundamental to that. That's what kept my interest in these boring-ass problem sets, okay? So then you realize it's not about the problem set. It's about manipulating equations that exist only in the service of the problem you are reading. And so you build this inventory of things that can happen in the universe and the equations that matter to it. So if it's motion, right off the bat, I'm probably going to need Newton's laws of motion somehow. Right. Is it moving really fast? I better know Einstein's equations, okay? Is it dropping through a viscous medium, okay?
Right.
Oh, by the way, can I tell you, in high school, I didn't know what the word viscous meant.
What did you think it meant?
I got a 98 on my physics Regents exam, and I knew what question I got wrong because I didn't know what viscous meant. They said, plot the distance time curve for a rock falling through a viscous liquid. Had I known what viscous was, then it's trivial. Because what happens is you drop it into the liquid. Normally, if you drop something, it moves faster and faster, right? Because gravity is accelerating it. But in a viscous liquid, it just descends.
That's right.
Old timers will remember the Prel shampoo commercial where they dropped a pearl into the shampoo and it just gently descended. So what happens?
What did that prove?
I felt the same way. If something is moving through a fluid where there's viscosity,
Right.
then there are viscosity equations. And if I never did a problem set that involved viscosity, I would not know to reach for that formula or that bit of mathematics.
And that's a real world problem too, because
all of these become real world problems.
Yeah.
That's the point.
Yeah.
So every week there were typically 6 physics problems, each testing different for homework, each testing a different physical principle.
Right.
You'd have to apply a new formula you learned that week in order to solve it. And when I say formula, that cheapens it. You'd have to apply a new understanding of the behavior of nature that you learned that week. And here's the equation of that new understanding.
So that's your toolbox.
Toolbox.
Yeah. That's
Toolbox.
It, yeah.
Toolbox. So you look around and you say, wait a minute, there's matter becoming energy here. What's going on? Marie Curie, one of the first to show radioactivity is a source of energy coming out of nowhere.
All right.
All right? There's no machine or engine going in. What's going on? There was no way to understand that without an equation that has energy on one side and mass on the other. There was no way. You can just describe it, but there's no way to calculate with it until Einstein in 1905. E equals mc squared. Oh my gosh, a little bit of mass times speed of light, which is a big number, squared, you would get a lot of energy out of that by doing so. So if you have gaps in your physics knowledge, there'll be some problems that are intractable to you.
Yep.
Now here's what I wonder. We're scratching our head today. What new physics lay undiscovered until it rises up and we say, that's the equation I need to figure this out that I've been scratching my head on for the past 10 years. Maybe the equation does not exist yet.
Ooh.
So we don't know the solution until we're faced with the problem.
Or if you're really clever,
Yeah.
people were simply not clever enough with the known physics to solve the problem. For example, superconductivity. If you cool down a metal of your choice low enough, then electricity goes through it without any resistance at all.
Right.
Whereas any wire the electricity goes through, there's resistance, which leads to what?
Heat.
Heat.
Exactly.
So it goes through and there's no heat. Oh my gosh, what is that? It's a purely quantum physics phenomenon. Was there enough quantum physics to figure it out? Yes, but no one was clever enough to figure it out. Okay? What they found was that as the electrons get colder, their wavelengths get longer because of the wave-particle duality.
Yeah.
As they get longer and longer, all the electrons end up behaving like they're one particle. because all of their
wavelengths
line
come
up,
together.
they come together. And as one part of it, there's no resistance.
They behave themselves. Yeah.
So the quantum physics was available, but no one was clever enough to know how to apply it.
Didn't know where to point it.
Where to point it.
Yeah.
Where to point the weapons.
That's a great example.
Yeah, great question,
All
too.
right, I have another question. This one is from Lane, one of our other producers. She's over in our LA office. With David Krakauer and Brian Cox, we learned about the two main pillars of emergence. It is something greater than the sum of its parts, and secondly, possesses a distinct language to describe the emergent behavior. The example David gives is how fluid dynamics, through its own formulas, can predict movements of groups of particles without needing to know about each individual particle.
Yep.
Given that we have a language for describing and predicting a person's volition that screens off the microscopic factors in someone's life, would that make free will just as real as fluid dynamics? Is free will just an emergent property of conscious thought?
So I love that interpretation of what's going on.
Yeah, that's
And just to remind people, in case but you can dig up the show, there are gas laws we might have learned about in chemistry,
Right.
which are macroscopic laws that describe the behavior of the entire gas. Okay, pressure, temperature, this sort of thing.
Yeah.
And they work. That's why we use them. And they're called laws. Those were discovered before we even knew about atoms.
Okay.
Successful laws of nature describing the behavior of atoms in this emergent way.
Right.
What they all do when they're sorted together as a blob of gas. That's remarkable. So I like the direction certain branches of research are going, trying to wrap their head around the meaning of emergence in understanding complex phenomena. And so, yeah, free will is emergent. It's an emergent feature of consciousness. I'm always been on the camp, even if it's not free will, if it feels like free will, it's free will.
Yeah. I think it's a fascinating thought experiment because you can say if it's not free will, it's still a choice that you're making. So maybe it's the freedom of the choice. But then if the choice is predetermined by other circumstances, is it really a choice at all? But if you alter the predeterminate factors that caused the choice, who's to say that you did that or did the circumstance do it? It's so intertwined.
Or did the gas law
or did the gas law of your brain do it?
Yeah.
You know what I mean? Like, did the neurosynaptic, gas law property actually cause this to happen? And I think that in some respects, there's evidence for it all.
Maybe
when you look at it.
Maybe the future of neuroscience, I'm just pulling this out of my ass now.
Go on, please don't.
Maybe the future is looking at the electrochemical state of your mind. Okay? Just the way we look at the pressure, temperature, volume, and we put those together with equations that give the future state of that system. So, will it expand? Will it contract?
So it becomes predictive.
Yeah. Maybe if we do a download of your electrochemical state, maybe there are macroscopic laws that tell you what decision is coming out of that state.
That'd be great.
And if that's the case, I can say, well, you have this much poverty, you grew up in this situation, a single parent household, you didn't have food, but crime candidate to be committed. What is it? More than half of people in prison
are illiterate
or come from poverty.
Well, that's more than
and those are correlated.
Yeah, they are. I was going to say illiteracy and poverty go together.
So you have the configuration that then makes the gas law prediction.
You're talking about mind reading. Just from being able to take that snapshot of
it's brain reading more than mind reading.
In the sense of being brain reading, mind reading, yes.
It's better than mind reading. It's brain reading.
It's brain reading.
Because the brain creates the mind.
Exactly.
Right.
So, yeah.
Wow. So then we're the Minority Report all over again, aren't we? The great sci-fi short story writer, Philip K. Dick. So in the Minority Report, there were these precogs.
Yeah.
So rather than doing a download off your brain,
there
are these precogs who were telepathic, basically.
Right, yes.
And so that's how they got into your brain to know what was going on. But same idea.
Yeah, it is.
Yeah.
Except that you're mapping the actual person's brain.
The actual.
Actually, this is better than precogs.
Oh, of course.
Because precogs only happen because an event precipitates their telepathic.
They're not going to know whether
foreseeing.
you're going to choose strawberry or chocolate for dessert.
Yeah, they can't do that. But with brain mapping, and also, you would be able to determine a person's possible path, but also equip them not to take that path.
But you might have to change the state of the system, like changing the gas. You'd have to change the temperature, the pressure, the volume, so that a different outcome would come.
Right.
I think once that state is established, it's going where it's going to go.
Right. Yeah. You can't steam clean with cold water.
Oh, good. What? That's your mama tell you that?
No, I just made it up.
Very good.
You can't steam clean with cold water.
Right. So, for example, the person who's just about to jump off the bridge, did they have the option to not jump off the bridge? I don't think so. In that instant,
I don't think they do either.
Right. So
and there's no ability to reset.
Correct.
At that moment.
Not in that moment. Correct.
Yeah.
So that puts a greater burden on society.
Yeah.
As treatment of people who have behaviors that are transgressive or psychopathic or sociopathic.
We should have that burden anyway. Unfortunately, we don't.
You're right. Right.
You know, and
more blame should be on the shoulders.
And if you know somebody who's in that position, believe me, intervene. Okay, you can do something, even though it may still happen. I mean, I've lost family members to death by suicide, and even despite the intervention. Right. But in one case, there was a ton of intervention, and the other case, it was like, damn, I wish I pretty much saw that coming.
You saw it coming,
yeah. So
let's try.
This is from Matt, the editor. He says, this is quite literally, and Matt, our editor. Yes. Mm-hmm. This is quite literally a burning question as it has to do with firewood. I once heard Neil mention in an explainer some time ago that energy of the sun is contained within the trees that we cut down and chop into lovely little pieces for the burning in our fireplaces. Yes. Can you expound on this idea? I found the fact fascinating and perplexing, but during a recent camping outing, I chose not to share it as I didn't want to sound like an idiot trying to explain this to my fellow guests as we enjoyed the sun's transferred energy via campfire.
Love it. Love it.
What a great question, Matt.
So you eat food that was once alive.
Mm-hmm.
Everyone does.
Yes.
Okay.
Plant or animal.
And plant was once alive.
Yeah.
Okay.
Yes.
If you eat plants, where'd the plant get its energy from?
The sun.
Thank you.
Okay. If you eat cow, where'd the cow's energy get its energy from?
The plants.
Plants.
And the sun.
The plants you fed it.
Right.
Okay. So we are solar powered through that tracking.
Of course.
Now, plants use the sun to build larger molecules that have energy contained within them. Mm-hmm. Okay? So the cellulose, that has energy. Cellulose burns. Paper burns. Mm-hmm. That's energy inside the paper.
Yeah.
What color does the paper turn after it burns?
Black.
Black. The energy is not just sitting there in an energy vessel. The photosynthesis takes sunlight and creates energy-dense molecules out of it. Mm-hmm. Now, here's the problem. Here's why we are not cows. Because cellulose has energy. We cannot digest it.
No.
So you have to be careful in your calorimeter experiment. You don't want to burn things that we don't have digestive enzymes to metabolize.
Right.
Yeah, if I took straw and burned it, it has a calorie content, but of no use to us.
Right.
Okay?
Yeah.
So it has to be stuff you can digest. Mm-hmm. Otherwise, the calorimeter experiment is not meaningful to us. It's meaningful for physics and chemistry, but not for us. All right. And so you burn it, it's solar power.
It is.
Look at that.
There it is.
All right, here we go. Here's one. Maybe it's an unknown answer. But how about this? I was watching a truck the other day.
Wait, who is this from? Who's asking this?
This is me.
Oh,
I was
question from you.
Yes.
A Gary O'Reilly question. Okay.
Yeah, I have pushed to the front of the line. I've just ignored the bouncer. And what's happened is a truck has passed me on the road and I'm thinking, wow, that really looks like it's heavy and it's loaded up with dirt. And then the thought pops into my head. How heavy is planet Earth? Is that a knowable?
Yes.
It is.
Yeah.
Go on then.
Okay. Earth is weightless. Astronauts in the space station who are orbiting Earth are weightless. Earth orbiting the sun is weightless.
Oh, that makes perfect sense because the astronauts are falling around the Earth. We are falling around the sun.
Yeah.
The sun. So Earth is weightless. Maybe that's not the answer you're wondering, but
No, but you know what? It's the answer. It's the answer I think most people, myself included, didn't quite see coming.
Yes.
you didn't see that coming. You didn't see that coming.
That's a great. I love that answer because that's the case. However, let's say that we fall into another planet.
Well, that's different. That's its force of attraction on you.
Right?
Okay. And yes, you can weigh the Earth that way. You can weigh a planet that way by asking it how much you weigh on that planet. But you're asking about the truck, Gary.
Right.
And there's a clever way to get the weight of something that has tires, if I may.
Mm-hmm.
Okay. All right.
Here's what you do. Look on the side of the sidewall and look at what air pressure those tires are under.
Okay.
Generally, the bigger the wheel, the lower the air pressure. I don't know for sure what truck tires are. They might be 30 pounds per square inch, something like that. Heavy cars are like 60 pounds per square inch. Your bicycle, if it's like a racing bike, is 90 pounds per square inch, right? So large tires tend to have lower per square inch. But so let me just pick a number and let me say just say 50.
All right.
Let's just say 50.
Oh, that's a good round number.
Just a nice round number.
50 psi.
50 psi. Then here's what you do. Walk up to the truck, not while it's on the road passing you, and get a tape measure and measure the area of each tire's contact with the road. It'll be like a square, because it's round and then it flattens a little. And that flattening will have an area, okay? It'll be like maybe 5 inches by 6 inches, let's say, whatever. And you multiply those per tire. So let's say it's 5 inches by 6 inches. How many square inches is that?
30.
30. And these full-size trucks have 18 wheels. So 30 times 18 is, let's just use round numbers here. Let's call it 20. So 30 times 20, that's 6,000.
Oh, 6,000.
Yeah.
Really?
No. 30 times 20.
That's 500. I mean, 600.
600, okay?
600.
So there's 600, we're very roundy here, 600 square inches of tire in contact with the road. If it's 50 pounds per square inch, multiply the 50 times the 600. And what do you get?
30 grand.
50 times 600 is 30,000 pounds. That would be 15 tons. That's a 15-ton truck right there. Or you could just read it on the side of the truck.
Right.
But on the side of the truck is its maximum gross weight.
Oh, I got you.
So
that's how much it's allowed to be. It doesn't mean that it's actually that weight at that time.
At that time. And the 15 tons would not only be the truck, but also the
tractor unit.
The cab?
The tractor unit, the cab.
Right.
Yeah. So that's because you did it for all tires.
Right.
Is the point
exactly.
there.
Yeah. But I see what you're saying, because the tire itself, the more weight it has, the more surface it will take up.
Correct.
And because of the change in that surface, that is how you can calculate the weight based on whatever's in there. It doesn't make a difference because you're going by that area.
Correct. And the old trick that any trucker knows is that if there's an overpass and you're like an inch too tall for the overpass, you let air out of the tires.
That's it.
And watch what happens. You let air out. What happens to each surface area?
It gets wider.
Yeah.
And
it gets wider, and you let air out. So you've reduced. So you've made the surface area greater and the air pressure lower.
Right.
So that when they multiply together, you still get the correct weight of the truck. It'll be correct every time.
Okay. That's cool.
All right.
We're going to do Alex. This is our boy Alex. I wonder which Alex. It doesn't say which Alex.
We have two Alexes. We have two
Alex. Oh, it's Alex P. It's Alex P.
Alex Picades, yes.
Yes.
Okay.
This is from Alex P., our producer. And he says, Google's new quantum chip can, in 5 minutes, complete computations that would take modern supercomputers longer than the age of the universe. Some view this as evidence of us living in a multiverse. What other proofs might cement the multiverse theory in your view?
Yeah, I think, let me restate what he's trying to say there. If we have that power, that means we have the power to create a whole very convincing universe within our computers. And you can create like Mario, the Mario universe where Mario has free will and is thinking complex thoughts rather than just trying to collect coins. And so I think that's where he's coming at. It means we have risen to the power of a civilization that can simulate other civilizations.
Right.
And maybe we have been created with the power to then reach that level as well, possibly implying that we are created.
A living in a simulation.
Yeah. And so we briefly hinted at this in an earlier recording, but it's worth repeating that when I don't know if you've ever programmed a computer, but when you do, up at the top, you have all these parameters. Okay. What's the value of pi? What is the value, what is the gravitational constant? And these are your variables that get preset right at the top. And then you just call them in any of your subroutines for when you need it. Okay. You reuse them, you calculate with them, but you have to set up something there. Okay. So how many digits of pi am I going to hand the computer for when I calculate with pi? When I programmed it, 6 digits was good enough. But if I want to feel luxurious, I'll give it 12. But pi keeps going. Okay? Now, suppose you measure something in the universe and it's only accurate to 12 digits of pi. And you make more measurements and it's getting the wrong numbers for pi. That would be evidence that you have reached the programmer's limit of what they established for your world. And that's like in the Truman Show, where he paddles his rowboat to the edge of the horizon and hits the wall. And there's a painted wall. And so this example's version of the painted wall is the limits of certain physical constants or other phenomena that have unnatural limits that you encounter. And another one was we have cosmic rays are formed by high energy phenomena in the universe. We see them. They arrive here on Earth and they come from halfway across the universe. You can measure how many cosmic rays have a given energy. Okay? So there's a lot that have this energy, and you go to higher energy, there's fewer and fewer. Okay? All right, just follow me here. You go to higher and higher, there's fewer and fewer. Suppose you get to a point where there's a cutoff and it doesn't sort of blend into nothingness. That could be the upper energy limit of the programmer. They're saying, they'll never get there. Let me just put this well beyond. And in fact, we've been humans for at least 100,000 years in our current form, several 100,000 years. So maybe the programmer had no expectations we ever come near that.
Right.
Yet we did. Because, 1,000 years unto us could be a day unto the programmer.
Yeah, exactly.
Right. However that biblical phrase goes.
Right.
So it could be that we start finding the limits in the universe, the measurable limits. And that would be a way to show that there's a programmer out there. Yeah.
Do you expect it to be infinite and just have no limits and just keep going on and on and on?
No. So I guess what I'm saying is in a software,
right,
you can't just put infinities in it because it has to hold it and then calculate with it. So you have to truncate it in some arbitrary place that you think is sufficient. So when I went to 12 decimal places on the value of pi in my programming, so I've written in my life about 50,000 lines of code, plus or minus. And in there, you've got your favorite variables you put in. I went to 12 decimal places because that's more accurate than anything we have ever needed to calculate out to the radius of the universe. So I'm good for anything I needed there.
Right.
So with my software, I was not likely to hit the limits of creation. But it's a way to think about it, for sure.
Absolutely. And we've discussed this on a number of occasions. We need to be thinking differently to solve problems that have so far stumped us.
Not only that, we need to be thinking differently to even know what questions to ask.
Exactly.
That we're not even aware were visible to us in plain sight because our brain wasn't ready to even think that way. I lose sleep over that.
All right. How does the debate shift when comparing AI that only imitates life to computational systems built from living neurons or biological substrates that may actually experience something?
Ooh.
What a question.
Wait. So the question was, how does that debate play out? What?
Yeah. How does the debate shift when comparing AI that only imitates life to computational systems built from living neurons or biological substrates that may actually experience something? Yeah.
Ooh.
Well, that's a wild question, but yeah.
Maybe I want to give a cop-out answer here.
Okay.
Maybe the distinction is artificial between those two. Maybe if something can calculate and can do things you need it to do, and it's way smarter than you, and it can answer all your questions because as the sum of the world's knowledge of all humans, and then you have another entity that can think up questions as well and respond to you. Like, does it really matter what it's made of? Who cares?
Well, it might. It might.
What you want to do, you want to measure, maybe philosophically for sure, but in practice, this is the whole point of the Turing machine. The Turing machine, which came out of his research paper called The Imitation Game, and the title of that paper became the title of the movie. Movie that starred Benedict Cabbage Patch, brilliantly acted, and the whole movie, an important slice of history there. Point is, in that research paper, he hypothesized, he suggested that a computer is functionally conscious if you can interact with it and do not know whether it's a computer or a human being on the other side of that conversation.
Yeah.
So then the race was on. How do we get to do that? We need a computer that understands language. We need a computer that knows what verbs and nouns and adjectives are, that can compose a sentence. We need a computer that can interpret what you said enough to then speak back with you. So when I was in college, I interacted with an early version of this, and this was an interactive computer that took some cues from psychologists. Okay. So you would say, "Dear computer, I'm not feeling too well lately. Tell me about why you think you're not feeling well." Okay. Right. Well, I'm having problems at home. Tell me about your mother and your relationship. So it knew enough to put words in a place and just come back to you the way a seemingly concerned psychologist would. And this got to a point where you did not know if it was a computer or just a concerned psychologist you were having a conversation with. And this, as far as I was concerned, fully satisfied this imitation game. And therefore, I did not know if that was a person or a computer. There's an early New Yorker comic that has a dog at a console, and there's a room of dogs on consoles. And one dog says to the other, this is early internet, so this is like late 90s, something like that. The good thing about the internet is no one knows that you're a dog.
That's funny.
Right. And so who cares if it's biological or neurochemical, neuroelectronic? I don't think it matters. All that matters is in the end is the behavior that you're interacting with.
So what about self-awareness? Because that becomes, so what you just described, the consciousness is no longer functional once it stops the interaction. Because if it's not being engaged, it's not asking questions. We ask questions irrespective of whether we are being engaged or not. We have questions of ourselves. We ask questions of the universe. We never stop asking questions, and we never stop having that conversation with ourselves. So that self-awareness is what we would say is a integral part of our consciousness. So what about that?
All right. So the self-awareness, if that only manifests to others, if they interact with you, then who cares? Whatever's going on in your head will never matter to me or anyone else in the world unless we interact. Or unless we interact with decisions you made in your own head because of your thoughts.
Right.
And so one of Isaac Asimov's 3 laws of robotics.
Okay.
I forgive me if I can't recite them in order precisely. One of them is no matter what, you will not harm humans.
A human being.
Yes.
A human being. That's the first law of robotics.
First law.
The second law is you will not allow harm within your power. You will not allow harm to occur to a human being.
Right.
So you will prevent it if you can. Third one is you will protect your own existence provided it does not conflict with law 1 or 2.
Right.
Okay.
So your self-preservation is contingent upon the protection of human beings as well.
In those 3 laws. So here you are thinking to yourself, I want to do this, I want to do that, I want to harm someone else. I will react when I see that engaged, but I'm not going to respond to your pure thoughts. There was a whole Twilight Zone episode on that, where this guy was flipping a coin and it landed on its edge. And at that moment, he heard everyone's thoughts. And, he walked into a bank and there was a bank guard. Banks used to have guards. There's a bank guard. And he heard the bank guard saying, when the bank closes, I'll take the keys and I'll steal the money from the vault. And I'll do that tonight. And so the guy's freaking out. He's calling the police on the bank guard. And then he learns that the bank guard just has these fantasies every single day.
Right, every day.
Every day. We all have thoughts.
Yeah. Right.
And so if he never acts on them, doesn't matter to anybody else. It's your own little world. So if I'm a computer and you're not talking to me and I'm not having any thoughts, what do you care? You want to go in and say one is conscious and the other isn't when everyone's interaction with them is no different? So I'm not, philosophically, I agree it makes a difference. In practice, I think it doesn't. That's my point. And the robot's going to want to protect itself. You can program into it that it wants to protect itself.
Right.
There it is. So
yeah, and so I see what you're saying. Like if I programmed into you compassion, and that by doing so, I pretty much anticipate all the scenarios where compassion should be shown, or I just make it a default setting where you show compassion even before you do anything else, which is, kind of an understanding and acknowledgement.
The thing is, everybody has to build in these guardrails. Everybody has to be the good actor, not the bad actor. And I don't think any of us in this conversation right now believe that is always going to happen. There'll always be a bad actor.
But Gary, that's true for humans. That'll also be true for robots.
It's got to be.
For robotic humans. If I program the robot, like Chuck said, one variant is hugely compassionate and another doesn't have the guardrails, that robot is going to do harm just the way humans do harm.
Right.
And what do? We arrest them, try them, put them in jail. So I think it's artificial to distinguish what you're made of versus how you actually interact with. And I'm going back to the Turing test.
Okay. The one thing I would say about the sort of artificial, if you want, silicon intelligence as opposed to a biological intelligence is the biological intelligence is generally a low energy intelligence, whereas the other is a high energy consumer.
No. So the high energy one, you're talking about all of the AI farms where they're high energy consumption.
Yeah.
What's happening there is they are mining the whole internet of all of its information. Mm-hmm. It is having way better access to knowledge than you do.
Right.
With your own lonesome self. So if
but
you
a human mind doesn't consume anywhere near that amount of energy.
But if you ask AI to think no more deeply about a question than an average human does, I bet it's not using much energy either.
Right.
Yeah.
Okay. All right.
That's what I'm betting.
See the point you're making.
I'm just betting that.
And that's when we'll start electing them to public office.
Is that a guardrail anyone's considered right now?
What?
That AI could not be or should be elected to an office?
Yeah, I think because AI can be programmed to be completely rational, in my experience, no one likes rational leaders because they're not as susceptible to emotional appeals.
Right.
And I'm not saying I want it that way. I'm saying this is my read of how people behave. It's like in courts, they want to bring in a jury that can be emotionally swayed by arguments from a lawyer, not because the arguments are so logical, but because the arguments
are emotional
and passionate towards the goal of the lawyer themselves. So it seems to me politicians need to be people who know how to listen to you and can internalize your feelings. That's how you get to vote for them. What you could do is have an elected official who has this emotional connection, but this should be at least one member of their cabinet that's a completely logical bot.
Now that's kind of cool. An advisor.
And it's a bot logical advisor. So you'd say, I want to do this, that, and the other. And you go up and say, what do you think of that?
And it says, that is a wonderful idea. However, you will be voted out.
Or that's a wonderful idea. You've already hit your term limits. Go ahead and do it.
Exactly. Right. Yeah.
So you got another one?
Sure thing. This is Peter from Legal, our business affairs.
Oh, person. Yes. Uh-huh.
Yes. Peter says, there's an old saying, the best time to plant a tree is 20 years ago. The second best time is today. With an
I like that.
Yeah, it's a pretty cool saying. Huh?
Yeah. Unless the tree's life expectancy is less than 20 years.
He says, with an eye toward a much needed future thinking effort that could begin today, if you were able to snap your fingers and make it so, what one thing would you change about the way children and young people are educated in the U.S. and even worldwide? In other words, where have we gone wrong in our approach to education, and what would you do to correct that?
Wow. Okay. So I have a lot of thoughts on this, and one day I'm going to write a book, an education book. Not yet, because it's still percolating.
Still, yeah.
I have a lot of ideas on this, but let me distill it down to just a couple of key points. One, we need to train people not what to know so much as how to think.
Yes.
How to see information and analyze it.
Yes.
Because we're valuing what to know. You either know it or you don't. Do you know it? And you perform well on Jeopardy. But real solutions in this world come less from what you know and more than from what you can figure out when confronted with a problem that is yet to have been solved.
Right.
All right. So in the workplace, here's an example, a little contrived, but it's an example. You hand a task to someone in a workplace. I'm a manager and I hand a task. And the two extreme responses. One of them is, this was not in my job description. I don't know. This is no. Okay. That's one. All right. The other one is, wow, I've never seen this before. Give it to me. I will see what I can do with it. These are two completely different pathways of employees in a workplace. One of them will ossify in place. The other will continue to ascend. Do you see a new problem as something that someone else should solve because you're not trained, or a new problem as something that you will gladly take on because you like solving the unknown? Schools should be taught as something where you solve problems more than as a place where you're just loaded with information. So that's my first point. Second,
amen to that.
Second, we need to have schools where at the end of the day, you are sad that the school day has ended.
Yeah.
You know, you're in class and you're looking up at the clock, can't wait for the buzzer to ring. At the end of the day, you can't wait for the day. At Friday, you can't wait until the weekend begins. At the end of a holiday, before the summer, even graduation day, that you say you are now graduates, and you toss your hat in the air and you're celebrating that you don't have to continue to learn when that was your only job, was to learn. Right. And I'm not going to blame you. So I'm not blaming students for this. I'm blaming the school.
Right.
Because what's going on in the school where students can't wait to get out? And if what went on in the school was a celebration of learning, where your curiosity is fed every day, no one would want to leave school. You would want to stay in there and continue to be enlightened for every waking moment. A. B, it also means when you graduate, you graduate to a life of continued curiosity, a life of continued learning. And right now you have people getting out of high school. Let's say you don't go to college, you get out of high school, you get a job. Now you have just ossified in place because you are done learning. You don't buy any books. You got no curiosity beyond just your job's task. You want to be good at your job, of course, but there's the rest of the world that keeps moving because you were trained what to know, not how to think and how to be curious. So you got to change that as well. Last thing, I've come to learn that in a free society, you cannot legislate behavior in a progressive direction unless doing so can benefit you financially. Okay?
True.
So, you don't want to integrate the lunch counter at Woolworths? That affects your bottom line. In order to make the change, I could not have convinced you just by conversation. I had to hit your pocketbook. And I hit your pocketbook. Oh, the lunch counters are now open, are now integrated as they needed to be in the 1950s and early 60s at F.W. Woolworth lunch counters. They each had a luncheonette within the buying floor of the store. So consider when whaling was a big business. Okay, we're going back into the early 1800s, let's say.
Right.
Whaling. Why did we hunt whales?
We were harvesting blubber, and
blubber.
Yeah,
exactly.
Yeah,
the blubber that keeps the whales warm, insulates them, because whales are warm-blooded, was a fuel source.
It's a great oil. Clean
oil for our lamps, everything. You could have started a movement back then, as some did, to save the whales. These big, beautiful creatures, and we're just slaughtering them for their fat. I mean, come on now. That didn't work until what happened?
Alternative fuel source.
We discovered oil in the ground,
baby.
That was safer and cheaper to process and use. Then the whole industry shifted.
All right.
And so I'm not going to expect you to just say to people in a free country that they need to behave in a progressive or green way. So I would tell the people, getting back to the question, I would tell people in the pipeline, in the educational pipeline, be inventive, economically inventive about how you can create solutions to problems that are not just emotional, philosophical, or even scientific, that are also economic. Because when you make an economic solution to something, it flies because everybody wants a piece of that. And that's just being practical here.
Let me then throw in the chatbots, because I can get the chatbot to do my homework. I can get the chatbot to write a paper. So are we going to see students not necessarily being in higher education in a bricks and mortar campus? They've got their chatbots and they do their learning there. Or is that taking them out of the knowledge?
Yeah. So here's the problem. Here's the problem. Okay?
Yep.
So let's go back to when, because I'm old enough to remember when the 4-function calculator dropped in price from $200 to $30. Okay, that happened relatively quickly, like within like a year and a half or 2 years. Over that time, the big question was, should we allow calculators in the classroom? And the answer was yes, because there's some things you're learning that were not as important as other things, and some of them is just drudgery work. Okay, like long division.
Yep.
Does anyone know how to do long division anymore? Like, when are you going to be somewhere where you need to do long division and you won't have access to a calculator? You're not going to be in caveman and you got to start a fire. It's, well, I need long division and no one taught me. So there's a place for that. And before calculators, we had slide rules. Yes. Were slide rules cheating? No, it was just another way to get to an answer. But you had to know your steps to get to the answer, because garbage in equals garbage out. So here's the problem with the chatbots, ChatGPT, etc. It is revealing to us that the school system values grades more than students value learning. And as long as that is true, everyone at all times will cheat on all exams.
Right.
To get a grade.
Right.
But if the system instead were who is learning, nobody would use the chat box, only just to help themselves to learn more rather than to as a substitute for their own ability to write or to know, because they themselves would want to learn, because the curiosity would be built in. And so until the day that happens, then teachers need to give oral exams. So we need a higher student to teacher ratio to make that happen. I grew up in public school, 32, 34 kids per class.
Yeah.
Private schools are between 10 and 15?
15 kids. Tops.
Yeah, tops. So that's the kind of ratio you need to give everyone an oral exam.
Yeah. And they get 2 teacher's assistants, by the way.
Right.
Yeah.
Right.
It's like you have the teacher, and then you have like Miss Betty, and you have, Miss Judy that help the teacher. And
Right.
and there's only 13 kids in the damn class.
So those are my 3 bits of advice there.
Okay.
4, when you include my comment about using AI to do your term paper. I have time for only a couple more questions. So what you got now?
This is Frank's burning question. And
Franck, that sounds French.
Frank. He's our editor, Frank.
Yeah.
And Frank says, "Hey, Frank here. I might be editing this video right now."
Oh, yeah.
It looks to me like this office is a vault to the universe. Talking about your office? Could you grab your very favorite item and describe it to us ASMR style?
Wow.
Look at that.
Mm-hmm.
Wow. But there's so many.
I mean, there's so much crap in your office.
Oh, my gosh. That means you're calling all my stuff junk.
Well,
That's
it's
what
not
you're doing.
junk, that's for sure. But I mean, some of it is junk. But
Okay.
it all has sentimental and personal value. Some of it has actual monetary value too. Some of it is, I don't want to put it out there, but some of that stuff in there thank God there's security.
Let's keep it simple, okay?
Okay.
Right here. Hang on. Okay. Oh, ASMR style. So, many years ago, the Planetary Society caught notice of me. They, co-founded by Carl Sagan, have a mission to promote the public's understanding and appreciation of space exploration, especially that of the planets. I was invited to join the board of the Planetary Society. That's when I met Bill Nye. He was a member of the board. That's where I met Anne Druyan. Anne is the widow of Carl Sagan, who founded the Planetary Society. Well, after a couple of years of that, the idea came up. Should Anne Druyan, who owns the rights to Cosmos, resurrect the series? She mentioned it. I said, I'd be delighted to help. I have modern insights to get a next version. She said, have you thought about being host? And I said, no, I don't want to be a TV star. She said, but you may be able to do this uniquely in the memory of Carl. So I said, okay. So I agreed to do Cosmos. Then, who was going to fund it? We went to PBS, and they said, we want to put in our own writers. And we said, no, we got writers. No. And so it didn't land on PBS. No, it didn't. Then Seth MacFarlane took interest in this because he's a science geek. You will know if you watch any episode of Family Guy. He's had like the whole cast of Star Trek, and he's got time machines and weather machines and all. Okay, so Seth MacFarlane says, why not take it to Fox? And we took it to Fox, and Fox said, we'll bankroll the whole thing. And we said, okay, what kind of control are you asking for? And they said, we don't really know how to make documentaries, so just do whatever you want to do. It was like, oh my God. So while that's happening, Fox acquires National Geographic. This gives Fox a world distribution for Cosmos to show up on TVs in 40 other countries in ways that would not have happened had it just been Fox, or definitely had it only been PBS. So I create a relationship with National Geographic. Then Cosmos ends, and National Geographic says, Neil, is there anything else we could do together? And I said, well, I got this podcast called StarTalk. And they said, let's put that on TV. And I said, whoa, you mean like a talk show on TV? I said, yeah. So we put StarTalk as the very first late night television science-based talk show. And it was nominated for an Emmy 4 times. 4 times. Now, why am I saying all this? Because right here in my hand is a StarTalk mug created by National Geographic. It's a huge beer mug. I think it holds a pint. It's a beer mug that has StarTalk on it and National Geographic that could have only come about because it went to Fox after Fox acquired National Geographic, which could have only come about because Seth MacFarlane's worked for Fox, which could have only come about because I became host of Cosmos because I was on the board of the Planetary Society. That is this keepsake right here. This is not a metal stein. It's a glass mug. Gary, I think it holds a full pint. That's what you guys do in the UK, right?
That's right, yeah. Might even be called a tankard.
Oh. So this stares at me on the shelf every day, packed with decades of memories that are the origin of its existence. There it is.
Right.
Go.
Dr. Tyson, how do you personally position yourself in relation to...
Who's this from?
Sorry, this is from Zhao, one of our editors. And
one of our editors, excellent.
Yeah. How do you personally position yourself in relation to religion? Would you describe yourself as an atheist or agnostic or something else? And depending on that position, how do you approach the question of death? Even if one is not religious, do you consider it possible that something metaphysical might exist beyond the physical universe? Or does science suggest that death is simply the cessation of existence? What happens to the complex thoughts, memories, and emotions a person developed throughout their life? I ask this from the perspective of someone who is strongly atheistic and scientifically minded, now facing an incurable illness. My father is suffering and trying to convince myself that perhaps there is something beyond. In light of this situation, how would you approach the question yourself, or what would be the best intellectually honest way to even consider, from a scientific standpoint, the possibility that something metaphysical might exist? That's a long question, but I think it's an interesting one.
Yeah. Well, Zhao, thanks for bringing us down.
I know. Scott. Damn, Zhao. Okay. A couple of things.
Yeah.
I recently learned that Stephen Colbert, who is himself religious, he's a devout Catholic.
Yes.
Devout Catholic.
Yeah.
Yeah. That he calls people who say that they're agnostic as having no balls. Okay.
Gotcha.
I would say there's an atheist without gonads because they're afraid to commit one way or another.
I disagree with that. I think a lot of agnostic people did believe in God and then realize there's not a lot there to hold on to, but they still want to hold on to it.
He just wants you to commit, right?
Yeah, he wants you to go one way or the other. Gotcha.
Yeah. So I'm a different kind of agnostic,
right,
based on what I've seen and what I've read. I call myself an agnostic only because the definitions of words are how people use them. Unlike what we normally think of as a dictionary defining a word, a dictionary describes a word as it has come into use. Okay? So, if you look at leading atheists of the day, Richard Dawkins, who's been on the show several times, you look at Sam Harris, and Christopher Hitchens, now deceased. These are leading atheists who each had atheistic books that they've written.
Right.
And you look at their behavior, there's a lot of their behavior that does not overlap with my behavior. For example, I will defend the use of AD and BC in reckoning years.
Mm-hmm.
For BC is before Christ, AD is Anno Domini, Latin in the year of our Lord. I will defend the use of that because the Catholic Church put the Jesuit priest on the case to figure out how to fix the calendar that was broken. And out of that came the Gregorian calendar, which all the civilized world uses. Mm-hmm. So I give props to where it's due. Whereas ardent atheists strip that from the calendar reckoning and use CE, Common Era, and BCE, before the Common Era. Who are they fooling? It's the same time frame. Okay, so this is a cleansing of the communication channels just to put distance between them and anything religious. That's not me. Okay, my single favorite Broadway musical is Jesus Christ Superstar. My single favorite choral work is Bach's Mass in B minor, with Handel's Messiah a distant second, but it's still second. Okay, Handel's Messiah is actually written in English. It was was it the King James Bible? But it was anyhow. I am not ardent against people who have strong or even mild religious faith. Not up in their face debating them this. Whereas all these other folks I just listed have debated devout religious people in their lives. That's not me. Therefore, I don't want to say I'm an atheist if by saying so you think I'm going to be like that. I need some other word that's softer than that because I personally am softer than that. And my best evidence for this was I had a friend of mine go up on the space shuttle, and on my Facebook page, I said, Godspeed, my friend's name, and STS. I forgot which, STS is how they numbered the space shuttle missions. And I said, Godspeed, space shuttle. People in the comment thread said, Godspeed, I thought you were an atheist. Complaining that I used that word. These were atheists trying to claim me. So that was very telling to me that there's certain behavioral characteristics that are expected. And to the extent that I do not fulfill that, I will not count myself among the ranks of atheists, because it's the behavior of the leading atheists that are defining people's understanding of the word today.
Yeah.
That's why I'm agnostic. Okay. And the only reason why. Otherwise, there'd be no question here. Okay. All right. Now, how do I deal with death? As I get older, I'm thinking more and more about that. And the last chapter of my book, Starry Messenger, Cosmic Perspectives on Civilization. You know what I'm going to do? I'm going to read you those last two paragraphs.
Okay.
And then that'll give you all the wisdom and insight you need to take to your father, speaking directly to Zhao. So I've thought long and hard about death. And I'd lean towards the scientific sense of death, where your state of non-existence in death is not fundamentally different from your state of non-existence before you were born. Think about that. Before you were born, you weren't saying, where am I? How come I'm not anywhere? You just had no existence. And my confidence in a non-existence in death comes from people who've had mini strokes. And with mini strokes, different parts of your intellectual functioning go away bit by bit. Your ability to recognize other people, to know where you are, to remember to eat, to speak. Do you have short-term memory, long-term memory? And these are neurosynaptic failures of the brain. So in death, where there is no neurosynaptic activity at all, to require of death that somehow your brain is restored into some newly functioning whole, for me as a scientist, is unrealistic. But that doesn't alter other thoughts that I have. For example, we are made, not figuratively, but literally, of stardust. We are of the stars. We are the same ingredients the stars are made of. Our ingredients came from the stars. So it's not just that we are alive in the universe is alive within us. And that's a gift of 20th century astrophysics to civilization that borders on the spiritual. Okay, so now, in death, you've got pretty much two choices in modern society. You can be buried, that's my choice, so that the energy content of my body, which is still there when you die, you have no neurosynaptic thoughts, but your molecules were built up from your lifetime of eating and exercising and the building of your organs and your muscles and other tissue. In death, those molecules still contain energy. If I'm buried and I decompose, all that energy gets absorbed by microbes, by flora and fauna dining upon my body, the way I have dined upon flora and fauna my whole life. In that way, giving back to the earth what I had taken or literally borrowed over my life. If you're cremated, the energy content of those molecules, it doesn't go away, it gets transferred to heat. This is what heats the air column over the crematorium. That then radiates infrared energy that was once the energy content of the molecules of your body, radiates it out into space, moving at the speed of light. So, if after someone has been cremated, you can keep a timeline. Where has their radiant energy reached by now? If they died 4 years ago, if they were cremated 4 years ago, they would have reached the nearest star system, Alpha Centauri. 20 years ago, you can look at a map and see where that has touched. So that in a way, you're still a part of the universe. You're still in the universe, just in a different form. In order to presume you are fully alive and functioning, that requires religion, which is strongly based on belief systems rather than on anything science would tell you about it. I'd like to end, Zhao, with a reading from the last several paragraphs of a book I published a couple of years ago, Starry Messenger, Cosmic Perspectives on Civilization. I'll be reading from the last chapter titled Life and Death. Do you really know how precious life is? The total number of people who have ever been born is about 100 billion. Yet the genetic code that generates viable versions of us is capable of at least 10 to the 30th variations. That astronomically huge number is a 1 followed by 30 zeros, producing 1,000,000 trillion possible souls. Each of us, for all practical purposes, is unique in the universe, now and forever. Being alive is the time to celebrate being alive, every waking moment. Along the way, why not strive to make a world a better place today than yesterday, simply for the privilege of having lived in it? On my deathbed, I'd be sad to miss the clever inventions and discoveries that arise from our collective human ingenuity, presuming the systems that foster such advances remain intact. That's what fueled the exponential growth of science and technology in my lifetime. I further wonder whether civilization's arc of social progress will continue with all its fits and starts, and thus reward any time traveler from the oppressed spectrum of humanity who choose to visit the future rather than the past. On the whole, I don't fear death. Instead, I fear a life where I could have accomplished more. An epitaph worthy of a tombstone comes from the 19th century educator Horace Mann. I beseech you to treasure up in your hearts these my parting words. Be ashamed to die until you have won some victory for humanity. Our primal urge to keep looking up is surely greater than our primal urge to keep killing one another. If so, then human curiosity and wonder, the twin chariots of cosmic discovery, will ensure that starry messages continue to arrive. These insights compel us for our short time on Earth to become better shepherds of our own civilization. Yes, life is better than death, but life is also better than having never been born. Each of us is alive against stupendous odds. We won the lottery only once. We get to invoke our faculties of reason to figure out how the world works. But we also get to smell the flowers. We get to bask in divine sunsets and sunrises and gaze deeply into the night skies they cradle. We get to live and ultimately die in this glorious universe. Zhao, your father needs you now. He, whatever are his ailments, he is not alone in people whose lives have been hit by disease, ailments, accidents, war, pestilence. Regardless, we are the lucky ones because we got to be born at all. So I spent a lot of time wondering if I had never been born. You have to be born in order to then die. So the birth is a privilege and so is the death, because that's the package of life that we're handed. And everybody else in that 10 to the 30th variations of the human genome will never know either end of that celebration of this universe.